Hello, everyone. My name is Mark Weber, and thank you for joining us for our What's Next in AI event. This is a 3-week virtual conference that we're kicking off today. Hello, everyone. My name is Mark Weber, and thank you for joining us for our What's Next in AI event. Technical difficulties. This is a 3-week. There we go. I was simulcasting myself from YouTube while I was speaking. So thank you again for joining us. This is a 3-week virtual event we're kicking off to focus on 3 key topics in AI. AI we can trust, AI we can scale, and AI we can reason with. I'll be your host for the next 3 weeks starting today, and I work for the MIT-IBM Watson AI Lab on the IBM research side of the house. And our mission is to do fundamental science and advanced AI research and also connect that science with real-world impact. And the primary way we do this is through industry and university collaborations. First between IBM and MIT, but also with member companies who you'll be meeting throughout this event. So to kick things off, I'm going to flip over to my slides here. And a quick disclaimer, this is my dog Lola. She may say hi during this event, and if she does, I apologize if it's a little loud. She's been my office mate here in Colorado, where I'm casting from, and she's a wonderful, wonderful coworker. But hopefully we'll go off without a hitch today. Okay, so before we begin, let's step in a time machine and let's travel back to 1955, summer of 1955, in IBM's Information Research Facility in Poughkeepsie, New York. At this time, it was 5 years after Alan Turing had written on machine intelligence, and the neuroscience community was starting to come together with the computing community to discuss the potential interweaving of these two disciplines. But no one had really put their finger quite yet on this idea of machine intelligence and where it would go as a field. Enter Nathaniel Rochester of IBM, who was the architect of the IBM 700 series, which was the first mass-produced general-purpose computer. And he invited a young assistant professor from Dartmouth to come spend the summer with him at IBM. And the two of them pulled in a couple of other luminaries like Claude Shannon and formulated a proposal to the Rockefeller Foundation called the Dartmouth Summer Research Project on Artificial Intelligence. And this is the first time that artificial intelligence, or AI, was coined as a term. And what's really interesting is that here in 1956, when this was actually done, the summer of 1956, the tenets that they laid out in this proposal were automation, language, neuron nets, theory of calculation size, self-improvement, and abstractions. These are many of the same tenets that we have today. And it really started by the formulation of this field as a scientific discipline that academics and industry folks could come together and work on over the course of the next 70 years. So here we are today. IBM Research has grown into an organization of some 3,000 researchers across 19 locations on 6 continents. So it's really a global scientific community that we have. And on the MIT campus, there's a deep investment, a long-standing investment in computer science and artificial intelligence, including the construction of our new office space at IBM Research on MIT's campus that we'll be moving into next year. Now, when we think about companies and where AI is today, there's some interesting data from IBM that is worth paying attention to. On the left-hand side, we see that 95% of companies believe AI is the key to competitive advantage, and yet only 5% have extensively implemented AI in their business and core operations. And this is a really interesting signal. Why is there such a discrepancy? I think our director, David Cox, says it really well. The problem with automation is that it's too labor intensive. The reality is that AI takes deep expertise to execute and develop in the real world. You know, when we go beyond, even frankly in the scientific community, it takes incredible amounts of work, but especially when we bring it into the real world, it really is challenging. And this is why tech companies are paying extraordinary amounts to try to attract AI talent. And it's very difficult for for most companies to afford the people that they need to implement these very sophisticated systems. So with that in mind, we've developed some adjectives around AI itself to make it easier to talk about and more clear what we mean when we talk about it. Narrow AI is kind of where we are today. It's powerful, but it's also brittle, expensive, and opaque. So it can win games like chess and Go, and even more, and do more sophisticated things with language. But really, when we try to bring it into even just one step toward real world settings for use, it can be very fragile and certainly very expensive to maintain. Broad AI is the next frontier. And this is where we are today. This is what is going to be the subject of much of our discussions over the next 3 weeks. This is AI that's robust, transferable, explainable, and scalable. It's AI that could make an impact, frankly, and we're right on the cusp of it in the scientific community, starting to come into the business community. And lastly is general AI. You can think of this as more of science fiction, complex, fluid reasoning and autonomy, similar to the levels of intelligence that animals and humans display. And some scientists say that we're going to have general AI by 2050. Really, this is just code for we have no idea. But you know, through baby steps, especially from broad AI, at least some of these capabilities, like fluid reasoning, can start to come online, perhaps even sooner than we think. So again, the focus for these next 3 weeks is going to be on broad AI, and 3 key themes we've chosen for you are AI we can trust, AI we can scale, and AI we can reason with. And within each of these, we're going to be talking about specific things. To give you an example and motivate the problem of today, which is in part of AI we can trust, let's just talk about for a moment about how narrow AI is today. Many people think that the image recognition problem is a solved problem. And this is in large part because of the success of models based on ImageNet, where we can very accurately recognize chairs, for example. But we produced a data set called ObjectNet that shows objects like this in other variations, such as being turned, rotated, or having a different viewpoint, or having it obscured by another object. And what we found is when this is done, performance falls off a cliff. Now any human, any person with like basic reasoning or vision can look at a chair and understand that it's a chair in many different variations. But AI can't quite do that yet, even though we've spent years and a lot of effort in these competitions trying to train these models. So there's something deeper going on that's broken in the way that we're approaching this. And this is just one of many, many examples of how brittle these systems can be and why we need to work on things like robustness if we're going to trust them, and also rethink the basic architecture itself that is underlying the task at hand. This is why, it's examples like this that make it so hard to differentiate hype and reality in AI. We can see results that were done over here, but the moment we try to bring it into a different domain or with a little bit more complexity, it just falls apart. And our role, I think, in this industry academic partnership and in this type of setting with this conference is really to help you differentiate between the two. And in reality, that line is quite blurred, so it's not always clear. And even for us internally, trying to figure out what can we do and what can we not do, that's a challenge. And this is one of the reasons we lean on research as the lifeblood of innovation, where everything that we do is grounded in peer review publications and work that is performed by the world's leading scientists at MIT and IBM Research. And the reason that we commit, and it's very interesting actually that the tech industry especially, but as well as other businesses, are now taking, instead of doing all their innovation in a proprietary, in a super closed setting, many of us are now coming out into the public conference circuit and publishing in the top technical conferences among our competitors and customers And I think that that speaks to a sense of collaboration, but also a sense of the challenge that has to be overcome, and the fact that no one company and no one institution can do it alone. And that's where I think the business comes in as well. So it's one thing to do scientific work in kind of a silo. It's another thing to invite companies to bring domain expertise from different industries where you're serving different groups of people all around the world. And that's a really important aspect of our lab, which is this membership program where we make intellectual property, institutional learning, influence of our portfolio, as well as an IBM support system on the business side, available to companies who want to innovate in AI with us. And to date, we have 6 companies. We're just in our first couple of years. These are all very deep relationships where we work very closely with these companies to help them connect with our portfolio of research that we fund every year and bridge it to impact in their businesses. So looking at the agenda, we've talked about AI we can trust, AI we can scale, AI we can reason with. Let me give you just a quick preview about what those are going to look like. And then we will invite our keynote speaker and our first speakers of the day to dive deeper into AI we can trust. So AI we can trust, we're going to focus on 3 key topics. Robustness, which is really about improving model stability against adversaries or change. Sometimes change itself can be an adversary, where the change in the data actually disrupts the model's understanding and can break at the time that you need it the most. Fairness, which is a very important topic. Most of our data is biased in some way or another. When it comes to things that affect real human beings, those biases and those outcomes are very important to pay attention to. And we want to imbue our models with human values, not just allow them to run amok. And lastly, people. Engaging with and listening to real people who will be impacted by these technologies is an important aspect of fundamental research, especially in healthcare, that cannot be overlooked in the technical development of these models. AI we can scale. Many of you have read about challenges of scalability in AI in terms of compute and costs and personnel, et cetera. There are three things that we're going to highlight next week, actually, to start addressing these. The first is neural architecture. So this is the way we build neural networks themselves, the way we understand neural networks in the trees and the tasks that are happening inside them, and how we can make those architectures more efficient to accomplish a given task with much less of the work. Learning to learn is really a broad category where we can think about how we do labeling, how we do supervision versus unsupervision, meta learning, and the geometry of information, and understanding the geometry of information to teach AI to learn faster and better. This is intuitive for us if we think about what school is for us. It's not just learning to memorizing, right? It's not just learning facts and figures and taking those into a catalog. We're actually in school, we're learning how to learn. We're learning how to learn quicker. We're learning how to pick up new things, how to pick up a book and read it. And this is what we need to teach our AI systems as well. And lastly, transfer learning. Humans can fluidly reason about things, repurpose information from one domain to another, and AI needs to do the same if we're going to make progress. Lastly, AI we can reason with. And this is really where that bleeding edge of broad AI starts to tip over into fluid intelligence in the long run. One of the most exciting advancements in the last couple of years is neurosymbolic AI. This is combining neural architectures with symbolic architectures, which are classically kind of 2 rival camps of artificial intelligence, and understanding how we can imbue AI with a deeper understanding of what things actually are versus more of a surface level understanding that is very brittle. Multimodal learning is about integrating different types of data. Again, something we do as humans all the time. We're constantly integrating information that come from radically different data sources. And we're going to see some examples, for example, of integration of video and language and understanding relationships between those and how each reinforces the other in terms of developing understanding. And lastly, causal inference. This deals with the fact that almost all machine learning today, virtually, is correlation based in nature, and there's many problems with correlations. They can break. As humans, we are constantly trying to develop a causal understanding of the world, cause and effect. If I do this, that happens, and so on. And that's how we engage with the world. And so we need to teach our AI models to do the same. So that is the lineup we have. Encourage you to stay with us today. Share on your social media so we can share this content with more people. And also tune in for the upcoming weeks ahead. We're very excited to feature a number of luminary speakers who are really leading scientists and experts in their discipline, as well as some member company representatives who will be helping us connect this fundamental science with the business relevance. So with that, I am going to switch over here and introduce our keynote speaker. Okay, Dr. Aude Oliva is the MIT director of the MIT-IBM Watson AI Lab and the co-director of the MIT Quest for Intelligence. Together, these are the university's flagship engagements for industry-university collaborations in AI research. So Aude is really at the helm of AI science for real-world impact at MIT. And in addition to this leadership role, Aude is also an accomplished research scientist herself at MIT's renowned Computer Science and Artificial Intelligence Lab, or CSAIL, where she heads the Computational Perception and Cognition Group. In recognition for her work, she has received an NSF Career Award in Computational Neuroscience, a Guggenheim Fellowship in Computer Science, and a Vannevar Bush Faculty Fellowship in Cognitive Neuroscience. Most important, Aude is just a wonderful person. And Aude, I'm truly honored that I get to work with you. Thank you for joining us today.
Thank you very much, Mark, for the very kind introduction. So hi, everyone. It's a pleasure to give you a quick tour of our MIT-IBM Watson AI Lab, an innovative academic industry partnership on artificial intelligence and its impact in the world. So our 3-year-old lab operates on a mirror leadership structure, co-led by our IBM research director, David Cox, and myself on the MIT side, an IBM chair, Dario Gil, and an MIT chair, Ananta Chandrakasan. So our activities are overseen by a steering committee that are made of MIT faculty and IBM researcher. And this mirror structure allows us to design a portfolio of AI projects that span the science and technologies of AI, keeping in sight the real world and societal impact. So the leadership structure is also mirrored in our research and application portfolio. Each of our 90 Q&A projects is jointly proposed and jointly executed by IBM research scientists and MIT faculty members. And we have a growing number of patents in a single year and hundreds of peer-reviewed publications, which show the pace of innovation, as we are one of the most published academic industry collaboration in top AI conference. With those 90 active projects, we can cover many basic science and application areas that are related to machine learning and artificial intelligence algorithms. And importantly, we have the flexibility to launch new projects at any moment in time. And as the pandemic hits all of us in March, we founded in April new project aimed at advancing AI transformative potential for society in the face of the pandemic. So artificial intelligence could really play a decisive role in stopping the COVID-19 pandemic. To give the technology a push, we launched research projects to target the immediate public health and economic challenges of this moment, as well as projects with a lasting impact on how we evaluate and respond to risk long after the crisis has passed. Another advantage of our approach that nurture a diverse portfolio and a constant flow of new projects is that we can identify in our portfolio emerging AI clusters which represent long-term direction for AI innovation. And we are launching this fall a few larger scale projects on neurosymbolic approach to artificial broad intelligence, natural language processing, and efficient energy AI that capitalize on the combined strength of MIT and IBM. In our large-scale project, we can take a multidisciplinary perspective on AI science and technologies. For example, taking insight from the biological system in performing tasks with little energy consumption to build the next generation of AI-powered hardware, design deep learning architectures that efficiently process information, and importantly, stay green. Looking at another slice of our portfolio, we are capitalizing on AI we can trust, as AI systems are increasingly being used to support human decision-making. Trust has many facets, and we take again a multi-pronged approach of projects that define the borders of what an AI should and should not do. First, we develop tools and knowledge on what it means to have a system robust, efficient, and trustworthy, with policy-aware explanation of AI, preserving privacy, quantifying the strength and weakness of a model before it is deployed, and looking into the inner working of neural networks to identify what it has learned. And in collaboration with the MIT Schwarzman College of Computing, we are defining principles of ethical and social responsibility of AI with a roadmap to integrate decision about ethics and risk into the machine learning pipeline. This includes designing goals with accountability in mind, being able to understand why a decision was taken by a system and trace its source, and being mindful of the impact of the AI system in our society at large. So Mark, I think you have a question for us now.
Our IBM research director of the MIT-IBM Lab, David Cox, to join us. David?
Hello.
Wonderful. Thank you for joining us. So David Cox is the IBM research director in the mirrored leadership structure that Aude alluded to. He is a computational neuroscientist and came to IBM a couple years ago to lead this lab from his position at Harvard. So David, thanks for joining us, and Aude, thank you for your comments. David, thinking about the spirit of industry-university collaboration and some of the topics Aude just laid out, what motivated you to leave your cushy job at Harvard University, and where you were leading your own lab, to come lead this lab, stepping into the industry side, putting an IBM hat on?
Yeah, I was really quite happy at Harvard, I will say, and in case there's any of my former colleagues watching right now, academia is wonderful. And certainly when I was in academia, I had a number of touch points with industry and real world impact. Like many academics, had corporate funding and worked with companies. My lab spawned a bunch of startups. But there's always a tension between research and industry and impact, where not for any bad intentions, but there's a misalignment of incentives sometimes, where it's difficult for academics to really fully understand what will make a big impact in industry, and it's likewise hard for industry to get something out of academic research that they can practically use. And that's led to a couple different kinds of pathologies, I would say, in the structure of academic industrial collaborations. In AI in particular, there's been an enormous, unprecedented privatization of the field. Many professors poached out of their jobs. There was a case where at Carnegie Mellon, an entire department was effectively lifted up and pulled, in that case, into Uber. And there's something sad about that. You're losing something that's distinctive and important about academia. And then likewise, there's plenty of money flowing from industry into academia that maybe doesn't necessarily, it effectively ends up looking more like PR or building goodwill to have hiring pipelines. It's less about impact. The reason that I left academia to do this job, and the reason I'm so excited and so pleased to be working with Aude, who I've actually known since I was a grad student at MIT. So it's a real pleasure to be back here again and working together. It's because we work together, because IBM Research has this, we're a 3,000 person global research organization, 75 years old, 6 Nobel Prizes, Turing Awards, you name it. Like we can understand each other, and we don't just give money to MIT and fund research. We work together. And that's really been, I think, the magic of this whole thing. And now the fact that we can broaden that and bring leaders in industry in, and the audience, you'll all hear from some of these leaders in industry and work together. I think there's a real opportunity to accelerate impact, and I think that's what's so exciting about this lab.
Yeah, it's well said, and David alludes to the fact that he did his PhD at MIT. I did an MBA at MIT and was a graduate researcher at the Media Lab while I was there. And in fact, many of us, including the chair of the lab, Dario Gil, our MIT grads, that I think for me, having been on the other side, having been on the MIT side and engaging with different companies from that side, that aspect does engender some trust, I think. And as we think about AI we can trust today, trust is really a human value, and it always starts with people who are working together and to build trust with one another. Aude, how in your position do you see, as I said, this human trust component play out as especially with regard to academia and industry, which can not always be in the same camps. Like a lot of the tech industry and a lot in finance and other industries come under fire in society. To energy companies, finance companies, tech companies come under fire at different periods of time, and we have a strong societal distrust sometimes in working with companies, and there's a fear in academia of being co-opted by those powers a little bit. So how do you, in your role at MIT, both Quest for Intelligence and MIT-IBM, how do you think about the trust component and the relational component of working with companies like this?
Yeah, thank you, Mark. Let's not forget that the company are actually hiring us, or they are hiring our students. So this is like sending a child to work somewhere. For us, our students go to work in our university, in company, and so on. So we do have this relationship that keep going for years and decades. And as AI and machine learning is being developed very, very fast, very high pace, and we keep in touch via the conferences with our former student or people in the field. So I've been in this business of computer vision and neuroscience for 20 years, but I have to say in the past 3-4 years, I see more and more interaction and collaboration and discussion between academia, governmental agency, and industry. So the trust is there because we are working together almost on a day-to-day basis.
Yeah, indeed, and I think that it's interesting to think about how those relationships, what makes those relationships successful. I know, from my time when I was a student researcher, a graduate student researcher, working with companies that could balance an interest with short-term impact, like, hey, we want to make progress toward a goal, while also kind of committing to that long view innovation agenda, which can be difficult sometimes in an environment, in kind of a instant gratification environment that we live in. It can be hard to commit to long-term innovation, but those are the ones that really move the needle and allow for step change opportunities, I think. David, in your experience, both either as an academic or now in your role at IBM, like, what's one of the exciting kind of step change opportunities you've seen occur, or that you see a current kind of in progress right now?
Yeah, I think there are many exciting step changes in AI, and I think we're all experiencing just how rapid progress is. And one of the things, again, that's so exciting about having an industry-academic collaboration is we're entering into a phase of the development of AI where neither party can really do it on their own, and that there's a need, or there's an opportunity to put resources, and resources ultimately that that could only exist within industry into the field of AI and bring all the great minds and the creativity of all the both the existing professors who've been there a long time, but also the students who just course through academia and spend the most creative years of their lives in many cases with all their enthusiasm, bringing that together with the resources of industry and importantly with problems of industry to really make things happen. And we're seeing that in terms of compute. Increasingly, it's it's necessary to have an enormous amount of compute to be able to move quickly and do this research. But at the same time, really grounding that with the real problems is huge. So I think we're going to see, we've seen a flurry of activity, particularly around deep learning, and the excitement is palpable. But I think the next step change we're going to see is really has to do with what you're going to see over the next today and the next 2 weeks of the session. How do we actually make AI take that next step change? In terms of trust, the trust in it, in terms of scaling it in such a way that it is really accessible, just to solve the problems we need to solve, and at the same time not cause, climate change to be exacerbated, and then finally building systems that are much more autonomous, and this will be the topic of the third session, where we don't need to sort of carefully line everything up and curate data. It won't be necessarily so much about data, but more about having intelligent agents that can get out there and help you solve problems and really work with people. So I think we're, many people talk about AI springs and AI winters, at times when the hype of AI gets away from the reality. And I think there's legitimate concern right now that, perhaps, the hype is so high that it's going to outrun what the potential is. But I don't think we're going to have that happen. I don't think we're going to have another AI winter. And I think it's precisely because we're all coming together and finding real value in this today. If we can do that, if we can actually figure out how to bridge what we have to what enterprises and governments and society need, I think it's going to be really an amazing time. And I think we're going to continue this journey of AI.
It's one of the most game-changing developments of the last 15 or more years has been the rise of social platforms, social media platforms, the way that they serve content, the way that media serves content and makes recommendation algorithms and advertising algorithms that draw on auction theory, and a lot of the algorithmic advancements that we get excited about paying attention to, like chess and Go and language. These are kind of the flashy things, but meanwhile over here, these more fundamental learning algorithms are really changing the landscape of how we interact with the world, how we send and receive information. And we've seen a lot of concern, with the release of the movie The Social Dilemma and discussions in the U.S. Congress about the role of these platforms. We're seeing a lot of social and civil angst about that really drives at the core of distrust in where the technology is today. We're in an election week, and the Social Dilemma came out this summer, and these things are top of mind for a lot of people. Without talking about politics specifically or any specific platforms, what are you seeing at MIT with regard to student and faculty attention to some of the problems that society is raising concerns about with regard to these types of attention not attention algorithms in the AI sense, but like algorithms that are designed to grab our attention everywhere, and how that ends up playing out in society and politics?
Well, as a neuroscientist, I'm very well aware of how information, visual or auditive information, can grab your attention, can even stress you, can overwhelm you, and so on. And as a research scientist, also working in machine learning, I do have worries sometimes that there is this mismatch between our knowledge of the human brain and what we can do, and the too fast development of those machine learning platforms. One issue with machine learning algorithms is that they are like a species of there's pieces of model, and they do tend to be developed very fast and to be put into society or into those platforms too fast. So this is where, certainly at MIT in the College of Computing, we are very seriously looking at integrating decisions about ethics, social responsibility, and risk into the machine learning pipeline of our model of our larger scale project. And this is a long journey. This is really a roadmap that needs to be defined, but it's really at the heart of our students and people that are actually working on AI model. It's very important to us.
Yeah, you brought up something that I remember David and I and our colleagues at IBM talked about when we first joined IBM, because a lot of us are actually in this lab, our new IBM research staff. And this move fast and break things approach that the Silicon Valley types have been so proud of for so long has really unraveled as a deeply problematic approach when it comes to building platforms that literally impact democracies. And in this case, the most, one of the most powerful countries, if not the most powerful country in the world. We've seen this play out, that the move fast and break things approach does not work. And in fact, like behind the scenes at IBM Research, when we first joined, this was something that we explicitly talked about, that, listen, we are not going to take a move fast and break things approach. At risk of being a little bit behind in the beginning on certain things, we're going to move slow and be intentional and prudent, because that's how we can win the race in the long term, in the sense of, not just for a company, but for society. Make sure that this is developed in a thoughtful and appropriate way. David, I know this is something that you're passionate about as well, and getting to work with you on a personal level, I think it's inspiring that we have leaders in business who are carrying values that go beyond business into everyday work. And we have a number of, you and I have had a number of different situations over the last 2 years that called on us to deploy ethics in a practical setting, and we can't necessarily talk about all of them. But one of them that did arise this year, that was public, was with the surge of the Black Lives Matter movement and the surge of awareness about racial justice. IBM was the first to step away and put aside facial recognition, and that was a big event that triggered other tech companies following suit and was part of this wave of change that happened earlier this year. I'm wondering if you could speak to IBM's decision to do that, and also to your personal thoughts on this type, what we were talking about before with social platforms, but also with racial justice and facial recognition and these types of systems.
Yeah, I think one of the things that's been nice about working for IBM is that, fundamentally in our business model is built on trust, really. Our customers rely on us to steward their data, to make the right decisions, to not endanger them in some way. We can't move fast and break things. We have to move deliberately and build and fix things where we can. And I think the whole discussion of AI ethics, that's I think in the last few years, the excitement of AI has kind of led to a little bit of a hangover where some of the really aggressive, fast-moving progress, but and enthusiasm, and in many cases well placed, has led to running ahead without considering the full picture. And I think what's emerging now is a new kind of discipline that needs to be around AI. And we've really enjoyed and have valued having a partner like MIT to have those conversations with, because it's not just about us, it's not just about our customers, it's about society at large. And having a deep bench of ethics experts, different perspectives we can draw on. Internally within IBM, we have an AI ethics board, which includes a C-level, our chief privacy officer is on our AI ethics board. We talk to that person when we decide, should we be doing this? And you know, the question of should we be doing this, and how should we be doing this, is a question that we take incredibly seriously. And we ask, you know, not just before we set out on something, but we continually revisit that. And you know, it's been really refreshing, actually, also talking to our customers and some of the member companies that you'll meet at this event. They're asking the same questions, and I think together we need to define. You know, we're already doing things, but you know, we need to keep building that up and strengthening that, and really asking, like, what is the process by which we understand, you know, the impacts of what we do, and the second order impacts and the follow-on impacts. We need to understand, how does our business model, you know, align or disalign to ethical questions. So we need to be continually realigning ourselves to do the right thing. Because as you say, the stakes are huge. You know, move fast, break things. Okay, that's fine. But if the thing you're going to break is civil society, that's not okay anymore. And I think it's actually incumbent upon every single AI researcher, every person writing code that's driven by data, everyone who's working on AI across all the companies, you know, not just IBM, you know, all of our peer companies, all of our competitors, all of everyone who's doing this in this new space, to really constantly be asking those questions. And this is ultimately something that needs to be part of the training of you know, AI practitioners. You know, just the same way that the Hippocratic Oath and medical ethics is part of the training, the professional training of physicians, and legal ethics is part of the ethical training of lawyers. This needs to be front and center, and you know, this is a commitment we share with MIT, and particularly the College of Computing. You know, this is in front and center, and I think we all just need to keep asking these questions, because the stakes are incredibly high, and you know, we also can't back away from the potential of AI. There's a real potential here to solve really important problems in our world, and you know, we're gonna use AI to solve these problems, but we need to be constantly evaluating and reevaluating. And I think that's maybe even the most important thing that we do as we decide what we want to work on.
That's well said, Dave. And it's interesting, you know, you bring up the incentives of a company like IBM, for example. You know, it's easy to kind of, I don't know, distrust, frankly, like the idea that companies are interested in society, right? It's like, oh, companies are interested in profit. Like, let's all be real here, right? But it's worth noting, like, well, let's look at any given company. What is its incentive structure? You know, if its incentive structure is built on trust, if its business model is built on trust, then indeed that helps kind of align the company's agenda to societies, whereas not all business models are the case. And Aude, you know, with the Schwarzman College of Computing, I believe, you know, ethics requirements are going to be part of that new that structure, that academic structure at MIT, which I think is wonderful. Well, thank you both for joining us today. We're going to see Aude and David at different points in the day, and including at the end of the day, to do kind of a debrief on the content of the day. But for now, we are going to transition and welcome our first speaker, who is, sorry, let me just pull up this information. Yep, so Lily Weng is going to be joining us now. Lily is a sixth-year PhD student at MIT School of Electrical Engineering and Computer Science. She's working with Professor Luca Daniel, and they focus on the problem of evaluating and quantifying the robustness of neural networks. Lily's going to explain to you why that's so important and what's involved. Lily has interned with IBM Research multiple times during her student tenure and has contributed significantly to one of our most productive MIT-IBM research projects on this important topic of robustness. Lily, thank you so much for joining us today to share your work.
Thanks, Mark. Can you guys see my screen? Thanks, Mark. So I'm happy to represent MIT-IBM Lab today to talk about our efforts on evaluating and certifying robustness of deep neural networks. So these are the joint work with my IBM colleague, Pingyu and Sijia, and also my advisor at MIT, Professor Luca Daniel, Akilan, Irene, and Jeet. So I'm sure you all know that deep neural networks are everywhere right now. For example, in the applications of computer vision, in the test of image classifications, and also in the autonomous driving, we use deep neural networks to detect a pedestrian and also to recognize the traffic sign. It's also very popular in natural language processing and speech, where we use it to do machine translation, text classification, as well as speech recognition. However, it's actually more popular than we think. It can be used in the applications beyond CV and NLP and speech, for example, in the medicine and biology, security, defense, finance, as well as robotics. Perhaps the most well-known deep reinforcement learning agent is the AlphaGo, which already compacted the world champion. Unfortunately, deep neural networks are not as robust and trustworthy as we would expect. In fact, it's vulnerable to even a tiny little bit perturbation in the system. For example, it's vulnerable to the adversarial perturbations when there's an attacker trying to attack your machine learning models in the deployment. There could also be non-adversarial perturbations like random noises, natural variations, and also you could have the model parameter shifts. This often happens when you deploy the neural network in the hardware. It's possible to have distributional shift where you have mismatch between training set and test set, as well as data poisoning in training set. So today, I'm going to share with you how we can evaluate the robustness for these three types of perturbations. So the setting is like this. So this is a neural network that operates perfectly, so you can recognize that this is an ostrich image. However, now we consider there might be an attacker in between, which can try to add an adversarial perturbation on your image. Or there could be the random noises, where there's no attacker, simply random noises. And the third one could be the natural variations, which we usually call the semantic perturbation. That is, you have some, for example, rotations or slightly lightness change, brightness change, or color change in your image. So the resulted image actually looks still visually very similar to human eyes, but now deep neural networks cannot recognize it anymore. You will think it is for example, it's a shoe shop instead of an ostrich. So here's how we define the robustness of deep neural networks. So here I plot the decision boundaries, and this is an ostrich example. So an attacker can try to craft a visually very similar ostrich image, but now it's a shoe shop. So the perturbed image now is a shoe shop example. And there might be an even stronger attacker which can craft an even smaller adversarial perturbation that's closer to the decision boundary. In fact, what the ultimate goal of an attacker is that they want to craft the smallest, the minimum adversarial perturbation such that they can fool the deep neural networks. And this is called, however, our team has been taking a different approach, trying to quantify what is the robustness of a neural network. So instead of using adversarial attacks, we propose that we need to look at this certified robustness region, the safety region, which is the green circle here, so that we guarantee there's no adversarial examples can ever exist in this safety region. And the way we usually characterize this safety region is that we will report the radius of the region so that we know how large the region is. And here are the challenges for measuring the robustness of deep neural networks. So If we want to find out what is the largest safety region, the safety radius, unfortunately, it has been proved it's an NP-complete problem. So it's very expensive. For example, it will take 3 hours for just one input on very tiny network, which only has 300 neurons. So many of our work is that we show that it's possible to find a non-trivial safety region, so a smaller region, but it's much faster. So just a taste of how much faster it is. So it can narrow down to like 2 minutes and seconds for state-of-the-art deep neural networks. So today I'm going to talk about our proposed solution for these 3 different types of perturbations. So for the first adversarial perturbations, we propose clever score, which is the first practical algorithms to evaluate the deep neural network robustness. And we also have another branch of solutions where we try to provide the robustness guarantee to certify the robustness of deep neural networks. And there we are able to certify the robustness for different activation functions, different kinds of popular building blocks, and also the recurrent blocks. For the second type of perturbation, a random noise, we propose proven, which is an efficient algorithm that can build on top directly on this worst case framework. So proven is able to provide you the probability certificate when the neural networks has random noise at the input. And so the idea here is that instead of having the worst case guarantee or 100% that there's no adversarial example in this blue region, now we try to relax the 100% confidence to some, for example, 99% of confidence, and then we show that it's possible to get larger safety region when you relax the confidence. The last perturbation that I'm going to talk about in our solution is the semantified neural network. So the semantified NN is able to certify the robustness for semantic perturbations like rotations, lightning, and color changes. So these are like a broad family that the semantified neural network can try to certify, and it's actually can build on top of our existing worst case based verifiers. So let me get a little bit more details of what is our proposed solution. So the first one for the clever score, the idea is that we show that the robustness radius, the blue radius R, is actually related to the Lipschitz of neural networks. So in the clever score, we propose a simple algorithm where it allows you to estimate the Lipschitz constant very efficiently for state-of-the-art deep neural networks by just drawing samples, the green points here. And with this, we're able to find out what is the radius, safety radius there. The second line of approach where we are able to provide a certificate of the robustness is try to leverage the structure, the architecture of neural networks. So we can try to look at the activation status of the neural network and categorize it into 3 categories. So we can categorize it as either activated neuron, inactivated, or if it's an uncertain neurons, where we try to use the linear lines to bound the nonlinear activation function. So if we do this, then we can propagate the perturbation from the first layer, the input, to the end of the neural network using the formula we derived in the papers. So here's a little bit of the experimental results. So here I normalized the L2 perturbations. As you can see, for the MNIST, it has the largest perturbation, and for CFAR ImageNet, it has much smaller perturbation, meaning that you need only an attacker just need this small perturbation to fool a neural network. And also you can see that the attack algorithms and our proposed clever score are very close, meaning that clever score is doing a great job on estimating the robustness. And the second experiment result is for the robust certification algorithms, FastLink. So we show that it's not possible to evaluate the largest radius here with the existing verifiers, while Fastlane is able to find the non-trivial safety radius. And using the linear programming approach is not feasible for like 4 layers or more networks. And so it's essentially showing that the Fastlane type algorithms is actually providing non-trivial safety radius while being much more efficient. So the second perturbation that we want to handle is the random noise. And Proven is able to allow you to calculate a probability certificate. So the key idea in Proven is that we can find out what is the probability of no misclassification by using the worst case algorithms and then use the concentration inequality. So if we do that, then everything from step 1, step 2 are almost the same with the original algorithm, like the Fastlane cron and search. And the only thing changes is that at the end, we will need to use the formula to calculate the probability and then iterate to find out what is the safety radius. Finally, for the semantic perturbation, we propose using semantified neural network. So this is how it is work. So the key idea of the semantified neural network is that we are able to express many of the semantic perturbations using neural network layers. So if we can do that, then you can actually insert a semantic layer before your original neural network, then everything will stay the same, meaning that you can use the worst case verifier that we already developed in Fastlane, Crown, and search, or other LP-based verifier, and then we can get a type certificate for the semantic perturbations. So this is just like a recap of the solutions and the topic that I have talked about. So we first proposed the solution for the adversarial perturbations, and we proposed Clever score to provide practical deep neural network robustness scores, and also Fastlane-like algorithms provide the robustness certificate. And for the random noises, the algorithm Proven is able to provide the probability certificate, and Proven is sufficient because it can directly build on top the existing Fastlane-like algorithm. Finally, we propose semantified NN to evaluate the robustness of semantic perturbation, like rotations, brightness, color changes. And it is very efficient in general because it can also tag along existing verifiers by just getting an equivalent neural network to transform the semantic perturbation. So this is the end of my talk. Thank you very much.
Lily, thank you so much for presenting. That's really great work, and I know that you've been working on this with a great cadre of colleagues at MIT for several years now, and delighted to officially welcome you to IBM Research. Lily has joined us as a research staff member as of last week, joining our MIT alumni community here within IBM Research and IBM. So thank you for doing this important work, Lily. I think it's been really inspiring to get to know you and your colleagues and Professor Daniel and others over the last couple of years. A quick clarifying question. We're talking about the robustness of neural networks, and you give several examples in computer vision, where in image classification and so forth. What about other types of neural networks doing other types of things in language or in time series and tabular data? Can these methods that you described, such as Clever, deal with other types of data structures?
Right. Thanks, Mark. That's a very great question. So the solution I propose here work on the classification task as well as the regression task. So it can work on for example, the convolutional neural network, recurrent neural network. So this type of architecture is not a problem, but depending on the task, the property of the machine learning task, it will be different. So so far, it's able to handle the classification task and also the regression task. So
I think it's not necessarily about the mode of the data as much as it is about the type of task that you're trying to perform.
Right.
Wonderful. And David, you know, as a director of the lab and as the person who hired Lily, I would love you to share what is it about Lily and her work that said, you know, in a competitive environment, there's so many great scientists out there. What was it that you saw in Lily and her work that you said, you know, we really need this person to join us at IBM?
Yeah, well, I mean, first of all, Lily is obviously brilliant, and we want to hire the smartest people. But I will say, in terms of topic area, this idea of robustness is so important and often overlooked in the enthusiasm for AI. So, you know, we're entering into a period of time where there are a number of threats and barriers to AI adoption. So Lily mentioned a few of these. I mean, some of it has to do with, you know, there's just noise in the environment. You have a sensor, it's got some noise, or, you know, there's variation in the data for a variety of reasons. And we have an interesting toolkit in deep learning where it's very powerful, but we struggle to reason about how it's going to behave. And particularly as you compose parts of systems together, it's hard to know what kinds of levels of noise or drift in the data. The world changes gradually and data drifts that we're able to tolerate. And when you can't be sure that a system is going to behave under certain conditions, it's very hard to confidently deploy it when lives are on the line, or the fate of your company is on the line. You need to be able to trust it and understand. And Lily's taking a really unique approach on two fronts. One is being able to certify. In a former life, I actually had a startup that was building electronics, research instrumentation. And if anyone who's ever built electronics before knows, you live and die by data sheets. These are pieces of paper that tell you how a component is going to perform. What range of voltages can this chip take? What kind of noise is it going to put out if you do this? Or like what's the capacitance? And those data sheets let you build miraculous things. You can build incredibly complex systems with thousands of parts. With neural networks, we don't really have a situation where we can reason about it. So being able to certify and say, this system we can tolerate up to this amount of perturbation, that's very powerful. And it lets us reason also about comparing two systems. Is this one more robust than that one? And it gets us out of this sort of test and try, or try and fly. We just, hey, we're going to put this out in the world and try it out and see how it works and correct if we need to. For many applications, that kind of approach isn't good enough. The second piece that Lily alluded to, which I think is really important, is we're entering into an era where, as we deploy AI systems, they're going to become vulnerable to attack. Bad actors who are purposely trying to subvert the system. And as Lily illustrated, the neural networks we have today are shockingly vulnerable to these kinds of attacks. And we see it very clearly with vision examples where you can take a picture of an ostrich and very subtly perturb the pixels and convince the neural network that it's anything you like. They don't look anything like an ostrich. But those same attacks work everywhere. So as you know, Mark, because you're involved in the project, you're currently in the lab, we're working, for instance, on building neural network systems that can detect money laundering. So you look at transaction networks, and you try and decide, hey, is this actor who's making these transactions, is this likely to be because they're trying to launder money and conceal the nefarious source of funds by moving them around in a particular way? We can build systems like that today. That can do a good job and can help out human investigators in detecting money laundering, and which is ultimately hiding all kinds of terrible crimes. But the problem is that we also know that we can build adversarial attacks against those classifiers. In fact, we've done it ourselves in the lab, where a bad actor could make very particular transactions in a very calculated way that evades detection of our classifiers. So if we're going to safely deploy these systems, we need to know how vulnerable are they to these attacks. And ultimately, we're going to need to be able to build new mechanisms. And this is, of course, a huge research program in the lab, build new mechanisms. And of course, Lily's also been doing great work, particularly in the area of deep reinforcement learning, of enhancing the robustness of these systems, not just saying, you know, the first step is to certify, to say how safe are we, and then the second step is to say, okay, can we expand that safety? Can we be more confident that the system is going to be robust? And you know, it's an incredibly fast-moving field. You know, anytime you have an arms race and adversaries working against each other, you know, you have very rapid progress. But I think the kind of work that Lily is doing is going to be absolutely essential for us to be able to move forward, deploying these systems in the real.
Thank you, David. Yeah, that's really well said. And you know, it's interesting to think about the robustness of machine learning models and deep learning models this year, especially because it's a time of dramatic change in society with, you know, the COVID pandemic disrupting our society and economies. So many of the machine learning models that were relying on historical data where that had never happened before. Were broken. And so, you know, you have different types of, as Lily said, perturbations. You have like, you have ones that are almost invisible, but can still throw off a model. This could be as simple as like in a vision task, for example, like maybe I change the lights or I change the camera that I'm using, and this introduces some, you know, noise that is imperceptible to a human, but actually can throw off a model that's never seen that before. But then you also have catastrophic change, you know, things that dramatically change a system. And I'm wondering, Lily, like, do these scores, do these certifications that you're providing, can they estimate robustness to catastrophic change and dramatic change as well, or is it just these very minor type changes that it works for?
Right. So essentially the bound we calculate is more telling you that what is the tolerance of your machine learning system. So if you have a catastrophic change that's actually having a magnitude larger than that, then we say that we don't guarantee it's safe. So the score we provide is more like an index or the metric for you to understand what is the noise tolerance ratio for your current machine learning model.
I see, yeah. And that makes sense. I mean, even as humans, it can be hard for us to reason about catastrophic and dramatic change in the system. It takes us time to adapt, and some of our modes, you know, our modalities of understanding do break, and it takes us time to catch up. So it stands to reason that AI would have the same challenge. It seems to me that, you know, in the very basics of data science and like training sets and test sets and out of sample, you know, we have certain processes that are in play to when we develop any given model to try to understand how good of a model of the world it actually is, right? To me, it seems like a no-brainer that things like this, you know, robustness scores or, you know, clever, should just be part of the data science toolbox, just part of the standard data science process for machine learning. David, you know, how do we get there? How do we get from, you know, a paper that Lily and her colleagues wrote, you know, an algorithm that is useful, to actually being able to be implemented as a best practice is something in industry and data science that is just a no-brainer. People don't even think about it. You know, they just do it because that is a standard aspect of building good models.
Yeah, I think it boils down to engineering discipline at the end of the day. So, you know, if you've been in the software industry for a while, you know, at least for a couple decades, you saw the rise of what we call DevOps, development operations. The idea that, yeah, you're writing software, but then there's a discipline about writing, deploying, QAing, redeploying that you just have to do. Like if you don't do it, the complexity and error proneness of software is just going to eat you alive. We're in a little bit of a Wild West phase with AI where we don't have that yet, but everybody needs to be doing it. And you know, we variously suggested it should be called model ops. You know, the idea that there are actually lots of different stakeholders who need to be engaged with the model. And importantly, it's not just you deploy it once, you do something and you certify it and then say, okay, it's fine. It's a continual process of continually evaluating and reevaluating these models. And, you know, IBM, of course, you know, we deploy AI systems at scale in enterprises. So, you know, not surprisingly, we have products and a perspective on how to do that. There's something called AI OpenScale, which is a framework for deploying systems, and a framework for automatically checking, including things like bias. Do automatic bias checking. And of course, there are other examples of these kinds of systems from other companies. But the idea being that there's a continual conversation where we continually deploy, check, recheck, redeploy, and a discipline of kind of moving that around. The other thing I will say about it too that's important about work like what Lily's doing is sometimes the answer may be no. Like the answer may be do not use AI to do this because we cannot guarantee in this particular setting that this is appropriate. When you think about things like autonomous vehicles, those are we're racing into a situation where we're deploying autonomous vehicles. IBM doesn't really play in that space, and that's fine. But this is perhaps going to be one of the first widespread real world deployments of computer vision. And it's scary to think about what will happen when adversaries try and mess with things. I mean, there have already been examples of people, for instance, having a pulse laser that tricks your LiDAR into thinking there are things in the environment that don't exist, and that's attacking directly at the sensor level. But as these systems are using neural networks, the idea that we could very carefully craft inputs that would trick the system into thinking that stop sign isn't there, for instance, poisoning, which Lily mentioned, where if a bad actor can get bad training data into the training set, then you can basically build in little backdoors that can trick the system later. That's scary because a lot of the systems that we use are trained. Oftentimes, what people will do, they'll take a pre-trained model off the internet and then fine-tune it for their purposes. But the provenance of the data that went into that system isn't always clear. And even just tracking the provenance of a system within a company is a very complicated thing. So having the ability to track all these things, so that you can understand where it came from is one thing. But oftentimes the answer will simply be, hey, this is a dangerous thing. We shouldn't use AI at this moment. Or if we do use AI, we should use AI and include people in the loop in interesting and important ways. And that's ultimately going to be the discipline that we need to all have. We're constantly asking those questions about, is the system robust to the kinds of natural noise we might see? Is the system robust to the kinds of attacks that we might see? Like, what's the threat model for the deployment of the model? These adversarial examples aren't relevant for every problem. If the data is going to be internal and perhaps a medical setting, it's a little bit unclear how you're going to get an adversarial example against a chest X-ray or something like that. But in other settings, it's very real. And I think having a robust research program around this is absolutely essential for us as a company moving forward. And then having that robust discipline about model ops is going to be absolutely important for businesses that are trying to put this in the real world.
Yeah, that's well said. It's a good reminder for us. One of the things we're working on with our advanced prototyping team at the lab is developing DevOps for research and or ResOps and incorporating Lily's methods is something that we should bookmark. So for my team listening out there, let's make sure we do that. Well, thank you so much again, Lily, for sharing your work with us. Thank you, David, for helping us think about it in the context of bringing it into the real world setting. And it cues up, what you talked about cues up our next speaker very, very well. So next we have Dr. Armando Solar-Lezama, who is an associate professor in MIT's Department of Electrical Engineering and Computer Science. He is also the associate director and chief operating officer of MIT's Computer Science and Artificial Intelligence Laboratory, known as CSAIL. He leads the Computer-Assisted Programming Group, which focuses on the intersection of programming systems on the one hand and artificial intelligence on the other. So with program synthesis, it's all about the use of automated reasoning and learning to bring more automation to the programming process. And on the code side, on the other hand, code provides a versatile modeling mechanism. So program synthesis can play a powerful role in helping us build learning systems that are more predictable and robust. Armando, I think this intersection of programming systems and AI is really important for our theme today of AI we can trust. Thank you for joining us.
Thank you. Thanks a lot. So I want to talk a little bit about the challenge of AI safety, right? So at a very high level, a lot has been said about just the challenge of building autonomous systems, and especially autonomous systems that have important learned components that we can trust our lives to, or that we can trust our capital investments to, right? This is really a really big question and a really big concern. And so the question is, how are we going to do this? So the traditional answer to making sure something works is you test it, you test it, you test it, you test it again. You test it in all different conditions to make sure that it's going to work. And testing absolutely has to be a critical part of any attempt to making sure that a system that you're going to deploy is going to be safe. But it cannot be the whole story. For example, in the context of self-driving systems, right, people have pointed out that if you really want to be able to show that the systems are going to be safe, just the number of miles that you have to drive them to test them is enormous, in the hundreds of billions of miles. And not only that, but every time you make a change to the system, you have to validate that change. You have to test it. You have to essentially run the whole process all over again. So clearly, that is not going to be possible. Now, coming from the world of formal methods and programming systems, for us, the natural answer is verification. And indeed, in the last few years, verification has moved from a niche, esoteric thing that people in universities do to a real tool that is deployed and used by companies to really make sure that critical parts of their software are going to work as expected, right? So verification has made great strides in the last few years. But when it comes to dynamical systems, when it comes to these kind of, for example, complex cyber-physical systems, you're going to start running into issues. And to understand why, it's useful to think about how people do verification. Some of these great and exciting success stories in verification generally rely on two broadly distinct classes of approaches. On the one hand, you have very expert-driven approaches, where the recipe, roughly speaking, is you get an expert who really, really understands the problem domain, really, really understands the solution that you're trying to implement. And this expert really needs to understand exactly why this piece of code should be correct, right? Why do you think that this is actually the correct thing to do? And then this expert is going to spend a lot of time with a proof assistant to walk the proof assistant step by step through this correctness argument, to convince the proof assistant that yes, indeed this piece of code is correct. And at the end of the process, the assistant certifies that, okay, I am convinced, yes, this artifact is correct. This very intricate argument checks out, and this is a correct piece of code. So clearly, that is not an approach that is going to work when we're talking about systems with learned components, where who knows what this neural network actually learned, where you don't have the kind of structure in the solution that we normally leverage in order to make these arguments about correctness. Now, there are automated approaches for verification, but generally these approaches tend to operate with very tight constraints and very tight trade-offs between the complexity of the implementation and the complexity of the properties that you're trying to prove. So we have very good systems for verifying pretty simple properties over even very complex pieces of code. And we also have techniques that allow us to verify some pretty complex properties over small, simple pieces of code. But none of that quite matches what we're looking for with these autonomous systems, where we want both the complexity and we want to check interesting properties. So we need somewhat of a new and different approach. There is also another challenge when it comes to actually verifying or establishing the correctness of these complex autonomous systems or these complicated dynamical systems, which is the challenge about the environment. So in traditional software, when we're doing analysis, when we're doing verification, it's generally a very self-contained problem. You have some property, like the program should never crash, which translates directly into a very specific set of requirements, like I should never write to a bad memory address, with a very clear definition of what a bad memory address is, or I should never divide by 0, right? And so that makes the problem tractable. It also is necessary, right? Because if you have some input that could make your program crash, if you have some input that could write to a bad memory address, even if that input is some ridiculously complicated input that you'd never expect to see in the real world, you still have to fix that problem, because sooner or later, some attacker is going to identify this vulnerability and is going to exploit it to take over your system. So it's both tractable and necessary to prove these properties. By contrast, when you're talking about autonomous systems and you're talking about these kind of dynamical systems, you might have a property like, I want to make sure that the quadcopter should never crash. But is it really necessary and is it really tractable to prove this, right? What do we mean that the quadcopter should never crash? Like, what if it's flying outdoors and then there's a tornado, right? Can we really expect it not to crash when it's flying in a tornado? Or what if it's flying indoors inside a building and then the building collapses, right? Are we really expecting that it's not going to crash in that situation? Of course not. But then what are the situations where we are expecting it to crash? And not only that, how do we characterize the environment where this quadcopter is going to be flying in order to make these kind of argument rigorous, right? And what if it starts raining, for example, right? That might change the dynamics of everything. Do we still expect it to work correctly in that case? How do we define this environment where we actually expect the system to work correctly? So what is the approach that we're looking at? So at a very high level, what we're looking at is an autonomous system that is acting on the world and making observations about how the world changes based on these actions, right? And we're looking at the situation where this system wants to learn how to act in the world in order to achieve a particular goal. So one really important ingredient of the approach that we're taking is that rather than trying to verify this potentially complex learned system, what we're looking is to have a monitor, a monitor that guards those actions that the agent is going to be applying on the world, to make sure that those actions are not going to put it in a dangerous situation. So the idea is that unlike the complicated controller, the monitor doesn't necessarily have to have all the complexity that is involved and really make sure that those goals are achieved and they're achieved optimally. It's really just trying to avoid catastrophic failures, right? And so what that means is that the monitor can be simpler. The verification problem on the monitor can be more tractable than in the system. Now, how does the monitor know that these actions are going to be correct? Well, it has to actually check them against a model of the world, a model that predicts how the world is going to react to these different actions, right? So the monitor is going to intercept these actions, and if it senses that the agent is trying to do something bad, it's going to intercede and it's going to modify those actions to make sure that the actions are safe. Now, it turns out making this work involves some challenges, and two really big challenges in particular. The first one is that the monitor has to know something about what's going on in the world in order to know what actions are good and what actions are bad, right? And the original agent might have had some really complicated perception pipeline, for example, to really go from the kind of observations that are at the level of pixels from a camera to the kind of observations that actually tell us what's really going on in the world, right? But in the monitor, we cannot really afford that level of complexity. So what we're really looking at is that we might not have as clear of a view of exactly what the state of the system is. Additionally, any kind of guarantee is going to be with respect to this model of the world, which is clearly different from the real world. And this mismatch can lead to false security. It can mean that, yeah, the actions look correct according to this model, but when you actually try them out in the real world, you fail miserably, right? And this is somewhat of a fundamental limitation of any kind of verification. You can only verify against some formal representation of reality, and that process of formalizing and modeling is inevitably going to miss out on some detail that might actually turn out to be important for making sure that things work, right? So how do we deal with that? So one way we deal with that is by embracing this uncertainty, right? And by making sure that the guarantees are not just with respect to one model, but with respect to the whole space of possibilities that are consistent with what we have seen. And we also need to be able to update these models on the fly based on new observations and new data. Right now, in order to make this work, two ingredients are really critical. One ingredient is that we actually need to be able to verify these models. And so for this, we're really leveraging this Chimera X infrastructure that Nathan Fulton has been working on for several years now, and that is able to do rigorous reasoning about this kind of dynamical system. It's actually able to give us formal proofs that that these monitors are actually doing the right thing and checking the right properties. And the other big ingredient is going to be program synthesis, right? Program synthesis is all about a class of techniques that are able to combine behavioral constraints about how a piece of code should look like with structure, how a piece of code should operate, with structural constraints about how it should look like, and generate a piece of code that does what you want. So by leveraging these in order to generate our models, we can potentially generate these models with small amounts of data. We're particularly interested in neural-guided program synthesis techniques, where you can take advantage of a corpus of similar problems in order to learn how to synthesize very efficiently and from relatively small amounts of data compared to a more traditional learning techniques, right? Moreover, one of the things that is very powerful about this approach is that we can synthesize monitors that can be useful not just at deployment time, but even during training, because even during training, it might be important for you to avoid catastrophic failure situations. And so finally, I want to wrap up just by showing you a little video of a demo of what this means in practice. So in this case, what we have is the agent that is labeled as VSRL is the one that is using this monitor to avoid the catastrophic situations, in this case, crashing against the trees or the moving obstacles. And so what we can see is that whereas the agent trained with more traditional reinforcement learning is actually getting into dangerous situations in every single one of these trials, the agent that is guarded by our verified guard is never actually having this problem. And so to conclude, AI safety is a process. There's not going to be a magic bullet that is going to magically guarantee that that something is going to be 100% safe. The real world is too messy and unpredictable for that. But ignoring safety is not an option. And the other really important point that I'd like for you to take home is that verification is going to look very different from what we know from the software world. We have to do things a little bit differently because of the complexities of dealing with these learned dynamical systems. But nevertheless, it's still a very powerful tool in our arsenal that we can use to increase our confidence in this kind of systems.
Armando, thank you so much for sharing. The demo you shared is very impressive. I kind of want to unpack it for a second to make sure that we understand what's going on. So people are very familiar with AlphaGo and chess and various systems that really rely on reinforcement learning, deep reinforcement learning, to do extraordinary things. You know, things that not too long ago we thought were kind of unsolvable or were the heights of human intelligence. And not only are AIs beating humans, but AIs are crushing AIs now. You know, it seems to be a snowball here. But if I understand correctly, and if we can kind of unpack what we're seeing in that demo for a moment, you know, where there's a drone trying to deliver a package, right? And there's two different types of RL systems. One is classical reinforcement learning, and the other is verifiably safe reinforcement learning. So the idea is that where classical reinforcement learning just runs trial and error, trial and error, trial and error, and there's a lot of error in there where things go wrong, and that's how it learns. The verifiably safe reinforcement learning never violates the safety bounds in the process of learning. Is that correct?
That's right. So even in the process of, so what you're seeing here is already after the two agents have been trained. But the thing that is very powerful about this approach is that even during the learning process, you can actually learn with the guards on, with the guardrails on. And this is going to help you make sure that even during the learning process, if the agent is trying to get into this dangerous situation, the monitor is going to intervene and save the day, push it, move it around the dangerous situation so that it can achieve its goal safely.
And yet it seems to have a fail point in terms of the monitor's prediction of the necessary intercepts, right? So as you said, we can't fully guarantee it because ultimately this navigation of safety, this navigation of danger in the environment is based on a model prediction of what is dangerous, or is it somehow hard coded, or is it both?
So in this case, what we have is there is this model for these agents and how they are going to move, but a key ingredient in this approach is that you don't want to hard code the model completely. You want to leave it open for the system to recognize, hey, something is going on here that is different from what my model predicted. I need a new model. I need a model that is consistent with all the situations that the old model got right, but also with this new observation that the old model got wrong. And so in that way, it's an iterative process constructing these models. You're never going to have a full guarantee that you now have the model, especially in the real world, that you now have the model that is going to perfectly predict what is going on. But at least what you have is the ability to, when you have something go wrong, because of this mismatch between the model and reality, you can react to that and make sure that that doesn't happen again.
That's very interesting. And I think that iterative approach and the ability to adapt is really crucial here. And it's for me, you know, I come from a bit of a finance and economics background, and spent a lot of time thinking about and reading about different analyses of the 2008 financial crisis, for example, and how, you know, many of our models were very off in terms of the prediction of risk that was kind of latent in our economy and society. Now, this is a much more complex system than a single model for a single task. But one of the most impressive analyses that I read was from Andrew Lowe's book, a professor at MIT, who wrote a book called Adaptive Markets, and he's reconciling a little bit this. You talked about the behavioral versus structural components of program synthesis. We see very much a parallel in the world of economics with behavioral economics and kind of efficient markets hypothesis as being kind of competing views of the world in terms of how we understand dynamics in the financial system. Andrew Lowe comes in and analyzes 2008, and he says, no, it's, both are right in a sense. Actually, markets are complex adaptive ecosystems. They're part of a biological ecosystem where there's constant change and adaptation going on. And so as humans, one of the most important things we do in our everyday lives is what we learn is iterative, right? We're constantly adapting. And if we have a fixed structural view of the world in terms of our risk assessments of what are the risks that are posed to us at any given time, we can quickly fall out of date, and then those risks can build up and become kind of catastrophic black swan events. And so this iterative approach is very interesting, and I wonder, you said something that I haven't heard before, and that's a neural guided technique. Thinking about not neural networks, not necessarily as whole dependencies that we create for ourselves and which can fail, but using neural networks as in a guided way, while still navigating and learning where these dependencies and fail points are that we need to avoid. Could you speak more to that, and maybe beyond this one example that you gave, how can we think of some of the principles of what you've been doing more broadly in other deployments of neural networks?
Sure. So I guess a couple of points. So one has to do with this. So in the real world, and with all its complexity and messiness, you can never guarantee that you're not going to fail. But you'd like to at least be able to guarantee that you're never going to fail in the same way twice. And so that if something goes wrong, you can learn enough from it that the next time a similar situation happens, you're not going to fall into the same pothole. There's
intuitive as humans, right? It's like, yeah, everybody makes mistakes, but we don't want to make the same mistake over and over and over again.
Yeah, exactly. And I think when it comes to the modeling aspect, one of the things that often happens is when there's a mismatch between the model and the real world. Sometimes the mismatch starts manifesting itself long before you get to the point of catastrophic failure, right? You start seeing that, hey, there's this thing that is happening that doesn't quite match my model, and but nothing has broken yet, right? And so what you really want to be able to do is you really want to be able to go in and build a new model and analyze the situation based on this new model before you get to this point of catastrophic failure, before you get to the point of no return. And so being able to do this synthesis of the models efficiently enough to actually be able to do this is critical. Now, about the neural guided part of neural guided synthesis. So one of the things that is really critical there is using the neural network not directly as the function that is going to make your predictions, for example. So using the neural network not as the model, but rather as the thing that helps you find the model. So the neural network is there not to make the predictions, but to help you build the model that is going to make the predictions. And so the neural network is there to guide that process of building the model efficiently. And it's taking advantage of the fact that presumably these modeling processes are not going to be one-off things. You're going to be building model after model after model, especially if you're in the setting where the model is this very adaptive thing that has to change on the fly. And so because of that, there's a lot to be learned, so that you're not reinventing the wheel from scratch every time you have to create a new model, but rather you can really focus your compute efforts on the parts of the model that are really new and different and specific to the situation, rather than, again, having to reinvent the wheel every time.
We can almost begin to think about these different neural networks and different models, that are different networks that play different roles as agents within a system that are, in coordination with one another to achieve a certain goal. And you said something on the topic of mismatch during your presentation I thought was very important to key in on and maybe end on today, which is, the topic of today is AI we can trust. In the previous session, David Cox pointed out, well, you know what? Sometimes AI just isn't the answer. If we can't get to a place where we can really trust it, then maybe we shouldn't be using it. You mentioned, at the same time, we're looking at different methods that can help us trust AI. Robustness scores like Lily shared, VSRL, verifiably safe reinforcement learning, like you've shared with us today. How do we avoid, as we use techniques for robustness and safety, how do we avoid that keyword that you said, false sense of security? How do we make sure that we are reasonable in evaluating our risk tolerance, and we're not totally kind of fooled by these models with regard to what the real risk actually is?
So that's a really good question, and I think there's two elements to it. So one, for example, when I talked about verifying these monitors, one of the things that is very important to keep in mind is that the verification can fail, right? And the verifier might just tell you, no, you just don't have enough constraints here to really guarantee safety. Right, and so it's something that really forces you to look back and say, well, am I really asking for the impossible here? There's also, and related to that, you want to be very aware of all the assumptions that are coming in to these verification process, because ultimately, just because something is verified doesn't mean that it's correct. It only means that it's correct relative to all the assumptions you made as part of the verification process. And so making sure and being on the lookout for when those assumptions fail is really important. And people in the community often make the distinction between verification and validation, right? So, and verification is about, does this system satisfy the specification? Validation is about, does the specification actually cover what I expect it to cover, right? Have I actually, do the properties that I claimed that the system should have, are they actually enough to get what I actually want when the system is running out in the world? And for that, there really is no alternative to actually testing things very rigorously in a wide variety of situations.
Yeah, and that fits into our theme. Really, a theme of the day is kind of how do we update our toolbox of standard practices? Things that we do when deploying. The AI is moving so fast that there are things such as in software engineering that we do as best practices in code, and that we wouldn't even think about deploying a system without a number of different checks and things that are done. AI is moving so fast that some of those checks have been overlooked, and groups like yours and Luca Daniels and others are really going back and saying, actually, hold on, let's pause a second and figure out, how do we make these things safe? How do we not only make these methods, but make them accessible to people who actually want to deploy systems safely. So thank you, Armando, for sharing your work with us today, and for being such a great collaborator within the MIT-IBM Lab. I know that you have a newly funded a project with us, and we're very excited about what you're going to do going forward.
Thank you. Thanks a lot. Really looking forward to continuing this very fruitful collaboration.
Likewise. Thank you. So next, you know, a nice segue to this. We've talked about with Lily about certifying robustness. We've talked with Armando about safe reinforcement learning, and next we're going to talk about algorithmic fairness with Misha Yurochkin. So Dr. Mikhail Yurochkin, or Misha as we affectionately call him, is a research staff member at IBM Research, and by far one of our most prolific scientists in the whole of MIT-IBM Watson AI Lab over the past couple of years. In the past year alone, he's published outstanding works on federated learning, scalable Bayesian inference, topic modeling with optimal transport, AI fairness, and more. But of all the things we could have asked Misha to speak on, we chose fairness because this topic especially needs strong technical leadership, not just moralizing and hand-waving on the abstract importance of algorithmic justice, but real algorithmic work that gets us to a better, more just place, despite the baggage of historical bias that we see in so many of our real-world data sets. Misha, thank you for joining us today, and even more so, I just want to thank you for devoting serious time to the topic of algorithmic fairness.
Thank you, Mark, for the kind introduction, and hello, everyone. So this talk is about fairness in AI, and in the previous talks, the previous speakers covered the problem of safety of AI, but this is not so much about the safety of AI. Safety of AI is more about sort of responsibly using AI. So it's more about the societal aspects of AI and how it influences our society. And the reason this topic exists is, I mean, again, is the faults of our society. So unfortunately, the issues such as racism or gender biases, they still exist, and they affect the data we collect. And although AI a priori is not biased, I mean, it is a mathematical model, but after it ingests all the data that we give it, it kind of picks up all these biases in the data, and then it tends to even strengthen them and amplify them in some cases, which is not good for society. It can result in immediate problems such as reputation damage or lawsuits for business, and of course, in the long term, it's just not where we want to go with AI. So I think that's the overall topic of today's event, is how can we harness this power of AI, which is great, but do it responsibly. And the fairness is one of the key aspects of this problem. So to begin, let's talk about what does it mean for an algorithm, for an AI to be fair. And there are two major definitions of fairness. And the first of them is group fairness. The main idea of group fairness is that the algorithm is equally good on groups of individuals. So suppose we have two groups of individuals, the white applicants and the African-American applicants that are seeking a loan approval from a bank. And what can happen if we do not take any precautions is that the rejection rate could be quite different on these two groups. And well, why is this happening? There is, to be honest, why is this happening is actually, I think, the whole separate topic that deserves a talk on its own. But as a potential cause, it could be so that the historical data that the bank used to train a model to make the loan, to assist in loan decision making, there were not enough successful African-American applicants, and as a result, the algorithm learned that there is a correlation between rejecting an applicant and their race. And so that's why we end up with such kinds of decisions where only 1 out of 4 African Americans are given a loan. So group fairness wants to prevent such situations, and something that satisfies group fairness may look like that. So it says, well, 3 out of 4 white applicants and 3 out of 4 African American applicants received the loan. So this satisfies group fairness criteria, and this is good. So group fairness is certainly useful, and it's indeed been studied quite well in the prior work. There are algorithms, quite a lot of them, that help to achieve group fairness. There are even legal regulations, specifically in the financial areas, that require companies, whenever they use AI, to satisfy those regulations, such as they basically some instances of group fairness. So while group fairness is relatively well developed, the other important direction in the algorithmic fairness research is individual fairness. So the message of individual fairness is that algorithms treat similar individuals similarly. So for example, we have Ryan that earns 50,000 a year and lives in a predominantly wide zip code area. And we have Terry that earns the same amount of money, but lives in a different zip code area. So these are the two individuals, and what well, we can see that they are really only differ in their name and their zip code. They do not differ in their sort of financial stability and credit worthiness based on this data. So this means that these individuals are similar. They're not exactly the same, but they're similar for the purpose of loan decision making. And what individual fairness tries to avoid is if the algorithm that we have makes a different decisions on such similar individuals. Instead, individual fairness wants the decision on both of them to be the same. It could be both rejections, it could be both acceptance, but it should be the same. And so the individual fairness is the focus of this talk. So I would like to convince you that individual fairness is also important, and it's something that we should pay attention when deploying AI in practice. So why individual fairness? So let's consider an example, and one of the goals of this example is to showcase the potential pitfalls of group fairness that can happen in practice. So let's say we're talking about sentiment analysis. So if you want to classify words as positive or negative. So the positive words are admire, adorable, and so on, and negative are aggressive, distrust. So this is our training data. This is not a very hard task. So we can use deep learning, we can use some advances in natural language processing such as word embeddings, and it's quite easy to get 95% test accuracy. Is the problem solved? Is the question. And we can, let's inspect a little bit more. Let's see what our system does. So what if we try to determine a sentiment of a human name? And we will have two sets of names. So one, the first set of names is the names more common among the European American population, and the other set of names is the names more common amongst the African American population. Okay, so let's create a box plot of the scores, of the sentiment scores. So the bigger, the more positive, the smaller, the negative, that the algorithm outputs. So if we do not take any precautions at all, we see that the algorithm that we have now, although it is 95% accurate on determining, things like such that the word joy is positive, it is also tends to assign much higher scores on average to the names which are more typical among white people. And well, we see a difference between the average scores. So this is already a clear violation of group fairness. And okay, so suppose we can fix that. So we obtained this group, a new classifier. So it is also quite accurate, and it is group fair, right? So on average, the scores for both groups are the same. Well, did it really solve the problem? Unfortunately for Tyree in the data set, it did not solve the problem because the Tyree's sentiment is still very small. So the algorithm thinks that the name Tyree has some negative meaning, whereas for Ryan, the algorithm thinks it has a positive meaning. So we see how much the sentiments for these two names differ despite the algorithm satisfying group fairness. And that shows a violation of individual fairness that we would like to fix, because what we want is that we want every name to be treated equally in this context, while of course maintaining the ability to distinguish the adjectives that have positive and negative meaning. So if we use the algorithm we've developed that we call sensor, we can actually achieve this goal. So the sentiments of names become all pretty much comparable. There's very little difference among them. So now this algorithm satisfies individual fairness. So, and it does also satisfy group fairness because the averages are pretty much equal. So the one thing we also should check is that, well, okay, does the algorithm still solve the original task of sentiment classification? And indeed it does. So the baseline was 95% accurate, and the sensor in this case is 94% accurate. The exploration of the trade-off between sort of fairness and accuracy and when it's necessary and when it's not, very interesting topic that remains outside of this talk for now. But what we see is that, well, 95 versus 94 is not perhaps such a big difference, given that we achieved a quite significant gain in the form of both group and individual fairness in this problem. So this suggests that the algorithm can actually be practical and can be used in real tasks. So, okay, how did we do that? So first of all, let's recap what does a usual AI do, right? So how we usually train our AI. Well, we observe some data and we update parameters and we just repeat the process. So that's what we usually do. So the main difference here when we train individually fair AI is that we want to train an algorithm that's not only accurate on the data we have, but also on all possible similar data. And we've talked about similarity before, and I will come back to it on the next slide. But the pipeline is as follows. So we observe the data, and then we generate similar data where algorithm performs the worst. So this little evil face indicates that we are actually in this step acting as an adversary. So that's maybe could remind you of the Lily's talk earlier today. So our goal is to find the vulnerability of the algorithm, but in the sense of fairness. So we are restricted to only finding something that is similar from the perspective of fairness. So once these vulnerabilities are revealed, we use them to strengthen the model. So now we update the parameters using not the data that we've seen, but using this worst case similar data. And then we repeat this process. And as a result, we will obtain the AI that is robust to these so-called sensitive perturbations. And therefore, it is also accurate on similar individuals. So what it means is that this step where we act as an adversary cannot really be performed anymore. So we cannot find the data that is similar to the ones we have, where the algorithm performs poorly because it performs equally well on the data we have and on all the similar data. So this is the algorithmic pipeline. And okay, so what is a similar data? And we've talked about how Ryan, that earns 50,000 and lives in a white zip code area, is similar to Therese that earns 50,000 and lives in a black zip code area. And well, these two individuals are clearly similar for the task of loan decision making. However, and it might sound actually quite intuitive that they're similar, but in practice, it's not so easy to determine this sort of similarity pipeline to find those similar individuals. It requires quite a lot of subject expertise because, of course, the data is much more complicated than just these two examples. It is quite time-consuming, and it could be quite difficult on some data types, such as images or customer records. We are not probably going to draw or paint new images, right? So that's not very easy to do. But fortunately, this is an active area of research in the academic community. So a lot of papers are coming out, people are doing work. Also in our lab at MIT-IBM, we also do some work in this direction. And we developed and published several algorithms that are practical, right? As we've seen in the previous example with names, that could automate this process with minimal subject expertise. So indeed, we were sort of the subject experts, although we are not, but still our knowledge was sufficient. And our techniques are also applicable to different data types. So the individual fairness is actually, we already have something that can work, and people are doing a lot more work, so this will only be improving. Okay, so in the final part of my talk, I would like to sort of contrast the group fairness and individual fairness a little bit. But so these two definitions of fairness, they seem quite different, right? And it might seem a bit weird that just the idea of fairness is kind of one concept, but why do we have such a different definitions? Are they really so disjoint? And it turns out that they are not exactly. So there is a way to go from one to another. And so one example here is, so again, we have some algorithm outputs on two groups of individuals, and the acceptance rate is 50% in both cases. So we satisfy group fairness. But unfortunately, if we consider additional groups, so subgroups in the data, so for instance, the top row of individuals that live in wealthy neighborhood, and the bottom row of individuals that live in low-income neighborhood. So the algorithm doesn't appear that fair anymore because the African-American applicants from low-income neighborhood basically never receive a loan according to this model. And this is a subgroup fairness violation. So enforcing subgroup fairness with group fairness, of course, is possible. So if you define, instead of 2 groups, we define 4 groups and use some group fairness algorithms, we can solve this problem. But this requires expert knowledge. And sometimes we won't be able to think of all possible subgroups where the model can discriminate. And so as the groups sort of become finer, we see how this becomes more related to individual fairness. So this is essentially how we can interpolate between group and individual fairness. And now suppose that this individual in a low-income neighborhood that received the loan is Ryan, and the individual in a low-income neighborhood that did not receive the loan is Tyree. And you can see that individual fairness will identify a problem, right? So it will say, okay, the individual fairness is satisfied. And so the main point is that we can use individual fairness to also enforce subgroup fairness, and it also may generalize to the unforeseen groups in data. And sort of to conclude my talk, I would just like to say that while I may be focused on showing the advantages of individual fairness, this was just to show its importance. And what I really recommend all of us to think about is to be more ambitious in trying to obtain fair AI. So, of course, we should continue using group fairness, but we should also include individual fairness in our set of tools when we try to develop AI systems that are deployed in practice and that affect human lives. And thank you for your attention.
Thank you so much, Misha. Very, very impressive. And to join us for our discussion on this topic, we have Dr. Sherif Botros, who is from Wells Fargo, head of marketing data. I'm sorry, head of head of marketing data sciences at Wells Fargo. And also another MIT alum. Sherif did his PhD in MIT in artificial intelligence before it was popular. You might have been in the height of the AI winter, Sherif, I think.
Yes, yeah, exactly.
And so he brings not only deep technical expertise today, but he also brings context in terms of the evolution of AI over time. So thank you for joining us, Sherif. The three of us actually recently wrote a paper together on this topic of subgroup discrimination and AI fairness in the context of lending, and thinking about lending in terms of outcomes that can be disparate across racial groups. Sherif, that collaboration between the three of us and one of your other colleagues at Wells Fargo, Vanya Markov, started as an internal paper that you were writing on fairness and lending as a briefing for your company. Could you talk us through what motivated you to write that? What did you kind of articulate in your first pass, and then maybe also just give us an overview of the paper that we wrote together?
Yeah, sure. Yeah, thank you, Mark. So I just want to make a correction. I'm now managing AI research, not in marketing anymore. So
got it. Sorry, I'll update your LinkedIn profile for you.
Yeah, I'm sorry I didn't update it yet. But one important aspect to make AI available for banks is to really meet the fairness criteria. Of course, robustness and fairness and explainability, interpretability, and so on. Those are all very important aspects for AI to be applicable in marketing. Especially when you start using big data. Like in the past, we build models all the time, and it passed fairness. We usually, the way we look at it, we don't look at just the algorithmic fairness, but we look at the whole process, which includes people in the loop. Like when we apply for a mortgage or something, like the algorithm will make decisions, but there is a person who looks at the output of the algorithm and makes the final decision. So at Wells Fargo, we look at the whole process of fairness, not just the algorithm output. And what made me focus on this area is I thought like exactly like what Misha described, that group fairness is actually lacking a little bit in, it's not really, it does not guarantee the fairness at the end. But this is what the regulators require, right? The banks, the disparate impact. There is another thing, like banks also look at kind of individual fairness, and like people who are similarly situated in the same situation should have the same output. Like people who have the same input should have the same output. But also this is not fair. To give you an example, people who have the same credit score, the credit score itself is not fair. For example, somebody who is not banking as much, or is not who doesn't have a mortgage, or a housewife, or like somebody who is like a secondary person in all the credit applications will get a lower score. And what we test in the bank is that if they have the same exact score, they should be treated similarly, but the score itself is not fair, right? Yeah. So those are the issues like we are trying to deal with in that we are thinking about in fairness. So I'm not sure, Misha, like if this approach of individual fairness will solve that problem. Like if the inputs are similar in a sense, how can you detect that that input is not fair by itself?
Well, so the approach we have sort of requires this notion of fair metric, the notion of similarity, and we also have a separate work about just learning that notion of similarity from data itself. So it could be provided by a subject expert, as in your case. So you say that the same credit scores means they're similar, or we could try to also get this from elsewhere, right? So we can maybe, instead of saying how like the credit score should define who is similar, we should maybe, so our approach can say the following. So we can define pairs of similar individuals. So we can look at two individuals. They could be, you know, they differ in multiple ways, not just the credit score, but we can somehow determine that they're similar, maybe because they both were like a success, like in the past, right? So it's historical data because they both were successful loan applicants, so they returned the loan on time. And so from such information of pairs of individuals who we believe are similar, we could try to learn a similarity metric that can be later used to enforce individual fairness. And that similarity metric could actually capture more sophisticated aspects rather than just the credit score. And so I think we made some progress in that regard. So we used some of those techniques actually in that example with names that I've showed in the presentation. And also I think this topic deserves more attention from the academic community. To be like our paper is called 2 Simple Ways to Learn a Fair Metric. So right. We were not shooting for the final answer. We were trying to say there is, you know, let's start somewhere. You know, like there are some ways to get this without using simple machine learning, just positioned in the right way. So I hope that now there will be more papers of, you know, more sophisticated ways to learn this fair metric coming out, and we'll eventually move towards something quite advanced that can, you know, capture these biases that you've talked about in the data when defining the similarity metric.
Yeah, you know, I was impressed in Wells Fargo, you know, joined the lab just about a year ago, and I was impressed that, you know, in our internal meetings, that fairness kept coming up, that Wells Fargo kept bringing up fairness to the forefront of the discussion in terms of things that are important. And I think about something we said earlier about in terms of the way that the scientific community engages with industry, thinking about incentive alignment. You know, and it's interesting to look at Wells Fargo's business model as a major bank, and to think about lending itself is like this tricky double-edged sword. You know, getting a loan can be a game changer for a person to get a house and have a roof over your head, or to get to get one's education, or to buy something that's important for your business, that's going to help you grow and make an income. It can also flip into kind of a predatory practice where we market things to people and get people on a track that is not good for them in the long term, and it kind of traps them in a cycle of debt. And this subject, especially, you know, following the 2008 crisis and the formation of the Consumer Protection Bureau, you know, this has been a hot topic for many years now. And I wonder, Sherif, like in your view, sitting in a bank, how, you know, what can we do technically and practically to help companies? You know, what can the scientific community and technology community do to help companies like Wells Fargo capitalize on the business opportunity of lending, while at the same time making sure that, you know, you're treated the same regardless of your race, and that includes the empowering versus a disempowering aspect of what lending can be. How do we make progress on that front?
Right, and actually you put it very well, that there are two aspects to it. Like, you can give credit to people who like really wouldn't be able to pay it, and it's unfair in that sense. That's why individual fairness is also important. Like, we shouldn't just focus on fairness and forget accuracy, or focus on accuracy and forget fairness. They are both kind of important. So it's not just to meet the regulatory requirement, but we also have to have like some common, like accuracy should be important to us, and also not use predatory techniques, right? So this is very important. And I think that one of the issues we face is that model developers most of the time don't have access to those sensitive attributes like gender and race and so on. And like, this is one that they are unobservable, or sometimes for privacy reasons we don't even collect them. You are not supposed to collect them. And this is one area where we struggle a little bit. Like, model developers have hard time, you know, guaranteeing. We use like proxies for those sensitive attributes like zip codes and so on. But this is one area where I guess maybe some technology, like maybe use like secure multi-party computation to build models, or things related to what Misha described, like already have some similarity metric that's outside what the developers do. Things like that are certainly very useful in that sense.
It's interesting, you know, from a regulatory standpoint, you're not allowed to consider certain protected attributes like race, but then at the same time, the Consumer Financial Protection Bureau issues racial proxies to help you make your algorithm, you know, guard against disparate outcomes, because they recognize that you don't have race in the first place. So it seems kind of dissonant to me, and it reminds me of this term that was once popular and now is just kind of largely discredited, called colorblindness. You know, people used to say, I'm colorblind, I don't see race. And now we have I think a clearer understanding that no, actually it's not healthy to not see race, because then what you're doing is you're dismissing the very real structural and behavioral and psychological biases that are associated with racial injustice in our society, that are, you know, that are historical and present today. And so in our daily life, we don't have the luxury of ignoring race and being colorblind, because we have things that we have to deal with. And it seems like the same thing in data sciences. You know, we have to be aware of race, so that we can guard against the historical biases that are distorting the model, our models today. Well, thank you so much, both of you, for the conversation and also for your collaboration with the paper. The paper that we're alluding to will be published in the NeurIPS Fair AI and Finance Conference, which will be on, workshop at the NeurIPS conference, which will be broadcast on December 11th. So we'll be releasing more information on that soon, and great to be collaborating with you guys, not only on this paper, but hopefully on many more works on this important topic.
Thank you, Mark, and thank you, Sherif.
Thank you, everyone.
Okay, next, very pleased to close out the day with Dr. Collin Stultz. Dr. Collin Stultz, who, among a lineup of extraordinary people today, he really stands out as for his ability to be a world expert in multiple disciplines, both computer science and medicine. An MD, PhD graduate of Harvard Medical School, Collin is a practicing cardiologist at Massachusetts General Hospital, which is one of the most prestigious hospitals in the world. And at MIT, he is a professor in the Department of Electrical Engineering and Computer Science, where he leads the Computational Cardiovascular Research Group. His group focuses on using computational modeling and machine learning to identify at-risk patients, and then, importantly, create optimal treatment strategies to help those patients. One of the reasons we love working with Collin is not only is he saving lives in his daily work as a doctor, but he's also making these fundamental breakthroughs that can help save lives all around the world. And we also appreciate that his work is relevant beyond medicine. So he's going to be talking about healthcare examples today, but we can think about patients as analogous to people in many parts of our society and economy and businesses, and thinking about how we manage risks and how we develop strategies to deal with those risks effectively. Collin, thank you for joining us, and thank you for doing what you do.
Good. Thank you so much. That was a very, very kind introduction. I wish I had it recorded. I'd play it for my wife when she's upset with me.
We are recording it, Collin, so we can play it for her.
Send me a link. So today, the title of what my talk was identifying unreliable predictions and clinical risk models. But in thinking about this, I really want to get across some broader ideas. So that the title is probably a bit more apropos. Clinically useful machine learning. What is it really, and how can it be realized? Today, I want to sort of give a backdrop about what machine learning is in the clinical space and present some challenges, I think, that make it difficult for a lot of the most sophisticated methods to be embraced by the clinical community, and has already been articulated. A lot of these concepts, I think, are applicable beyond the clinical domain. So let's begin with some terminology that we can all relate to. What does clinical decision-making look like in 2020? Well, there are two participants. There is the patient and there is the healthcare provider. Information is transmitted from the patient to the healthcare provider. This information comes in the form of what the patient articulates. It comes in the form of laboratory values that are obtained either in an inpatient or outpatient setting, variety of different data sources that are multimodal. And some continuous, some categorical, but it's a hodgepodge of very complex data. And the physician has to integrate all of this information to decide what actions are best for the patient. If the patient is at high risk of an adverse outcome, ultimately the clinician wants to give them medications and procedures that will lower the patient's risk. Very simple paradigm. But in any hospital, especially a quaternary care center like the Mass General Hospital, it's much more complicated in practice. This is a simulated patient in an intensive care unit, just to give a sense of the types of signals that the healthcare provider has to integrate in order to make clinical decisions. Now, because all individuals only can integrate a few concepts at a time, and really digest them to be able to make decisions, physicians have to prioritize the types of data that they receive. So they can look at the electrocardiogram and look at general features from the electrocardiogram. But each of the individual samples from the electrocardiogram we don't analyze. You know, whether the sampling rate is 500 hertz, you've got 500 numbers in a second. We don't process that. We sort of look at general overarching trends, and we have to do some feature selection to decide what to look at. The advantage of machine learning in principle is that it can integrate all of these data that are multimodal, come in different forms, and are at very high levels of detail to give summary information to the healthcare provider that is of prognostic significance, with the goal of minimizing bad outcomes for the patient. So length of stay in the hospital, for example, probability of being readmitted, complications from procedures, and generally making informed management decisions. Now, while the importance of machine learning in the healthcare sphere is widely recognized, it has not been embraced by the clinical community. So you'll find the literature is replete with examples of complex models that can do on a surface some amazing things. Can diagnose different types of cancer by looking at pathology slides, can look at the electronic health record and make predictions about who will live and who will die in some finite time period. But when you go into the hospital wards and you talk to the clinicians who are taking care of patients, they're not aware of any of these data. Moreover, even if they were, I would say that many of them would not integrate these methods into their clinical practice. It'd be hard to get them to do so, even given the phenomenal performance that is lauded in the literature. So why is that? Well, these models take lots of pieces of data, integrates them, and hopefully gives understandable information to the healthcare provider. But when you look under the hood here, because all the data are complex, the models are similarly complex. And just in particular, deep artificial neural networks are complex, contain many modifiable parameters, and are very difficult to understand by the layperson and healthcare provider in particular. So while there's a lot of promise here, I'm going to say that there's somewhat of a Pandora's box involved because of the mystery involved that is involved in using these data to get useful information. So we have a dichotomy here in terms of how these approaches are viewed in the real world. We have the computer science community. If you look at the literature and conferences that really are very enthusiastic by the promise of AI and what it can achieve. And when you look at the clinical community, there is enthusiasm there, but it's blunted with respect to what you find in the computer science world. And I would say that there is a healthy level of skepticism about how applicable these methods are in practice. So let's take a look at a deeper layer and understand really the etiology of this discrepancy. So the data scientist has some particular metrics of success that he or she uses. So whether a predictive model is suitable for clinical use, you want to look at some statistical measures of performance that are pretty common. Accuracy, discriminatory ability is measured by the area under the receiver operator curve, sensitivity, specificity, all things that we're very, very familiar with. But the clinical metrics of success are a little different. So in the healthcare sphere, accuracy or these other standard metrics of success does not always, and I would argue, nor should it ensure that the resulting model will gain clinical acceptance. Why is that? No predictive model is correct all the time. If the model were guaranteed to always be correct, we wouldn't be having this discussion. But that's not the case. And wrong predictions, unlike in other domains, have disastrous consequences for the patient. If you have a patient that is at risk of death, and a model, a high risk of death rather, and the model predicts that the patient is really at low risk, and there's an intervention that you can use to lower the patient's risk, you've missed an opportunity to save a life. So understanding how a model arrives at a particular result or why it arrives at a particular result gives additional data that the clinician can use to gauge his or her trust in a given prediction for a patient. Now, so what defines a successful machine learning model in the clinical space if it's not solely these statistical measures of accuracy? And I want to thank Jianying for bringing this paper to my attention because it codifies a lot of the concepts that have appeared elsewhere in the literature. So you speak to the clinician who works in this domain, they articulate, well, you know, machine learning studies should, if I'm going to really use it, should involve some different moving parts, satisfy different criteria. So the study design has to be valid. The patients that are used to train the model should look like the patients that I see. You know, the standard training and validation and a separate test set, optimized model selection, and then performance evaluation. And here is where the standard statistical measures of performance come into play. But then there's some other things: explanation, providing an explanation, and an end-to-end pipeline. These are additional things that others, you know, people in the ML sphere, this is all very familiar. There's really nothing here that's new, but it's these two concepts that people in the clinical world will talk about as being important. End-to-end pipeline to make sure that one has the code, can apply it in different scenarios to estimate how well it works. I think that's pretty self-explanatory, but what does this explanation mean? And this is something that's not spelled out in the paper or adequately spelled out in the literature. In the machine learning literature and in the computer science world, explainability has a very sort of well-defined notion. So it dates back to a paper by Zach Lipton in the Association for Computing Machinery, ACM. And there he articulates some things that I guess criteria of what makes really an explanation for a machine learning model. So there's got to be transparency, and these are very high bars. So what does transparency mean? Transparency means it comes in two flavors: simulatability and decomposability. The relevant verbiage: for a model to be fully understood, a human should be able to take the input data together with the parameters of the model and in reasonable time step through every calculation required to produce a prediction. That's quite a lot to say, and quite a lot to be able to demonstrate for the deep learning models that are being developed in for clinical applications. There are attempts to do hand wavy types of things in terms of text explanations, visualizations, local explanations, saliency maps, self-explaining neural networks. Don't do this in all of its glory, but they echo some of these themes. Now, in explainability in computer science, it's kind of think about it, and just what our intuitive notion of explainable means is a little different. So many of the methods that I've just described provide insight into what input features are most important for the model to arrive at a particular result. Saliency maps are, I guess, probably the oldest method. Here you want to classify a particular structure: a palace, a dome, monastery, altar, church. This was incorrectly classified as a palace. These are representations of saliency maps over the different types of classifiers. It tells you where the model is looking in order to classify it in a particular region. Now, telling us what input features are important or where the model is looking, is that really an explanation? Well, that's kind of a philosophical question, but in everyday parlance, it's a little different. I mean, do we really derive a deep insight into what the model is doing from these sorts of data? I would argue no. Myself and others would argue no. So other methods that exist in the literature, self-explaining neural networks, attempt to generate basis interpretable concepts, but they're difficult to explain to clinicians in their everyday language. So explainability in computer science, not only is it very different than explainability and what we mean in our everyday discourse, it's even a bit more problematic, because explanation methods that have been developed in the computer science literature, usually it's deemed successful if you can apply it to different data sets and demonstrate that it's explainable in some way. So you have some explanatory method, you can apply it to publicly available data sets, database of handwritten images, heights, weights, database of images. These are very distinct sets. So what you have in general is some method that is designed that fits all, that works in some sense across many divergent distinct domains. But in principle, however, for an explanation to be successful, it must rely on concepts familiar to the intended audience. And when you have an approach that you think works across many different domains, it kind of almost by definition does not heavily rely on the domain-specific concepts for any one domain. So it's really not a good explanation for any of the domains. So an example of this is, let's say you have a quantum physicist. So this is Heisenberg, and he is trying to explain to a literary scholar the concepts underlying the Heisenberg uncertainty principle. Well, he might begin his colloquy in momentum and position are non-commuting operators and therefore cannot be simultaneously determined with arbitrary accuracy. The literary scholar has no idea because they don't have a common reference frame of concepts. But if he were to have the same discussion with a physics PhD or a recent physics PhD grad, then he could successfully explain to this person, because the prior concepts that the physics PhD brings to the discussion are familiar to the prior concepts that the quantum physicist has. So one-size-fits-all approaches are doomed to yield explanations that are inadequate for many domains of interest because they are not ensured to leverage domain-specific concepts that are well known to the intended audience. So essentially, I know I'm running out of time, so I won't be much longer. So let's go back then and forget about explainability and these prior concepts of what makes a useful machine learning model. And let's start from scratch. Really, what makes a clinically useful ML tool? Well, let's start again with the clinician. Deep neural network. We said already, they're black boxes. It's hard for the clinician to understand what's under the hood here. But at the end of the day, the clinician has two questions. Even though the overall performance of the model is good, will it work for my specific patient? Is it appropriate for my specific patient? And is this model consistent with what I know about human disease? So I'm going to separate this into two very simple concepts that I think are metrics of success. Can I trust a prediction for a given patient? Will the model give me some insight as to whether this prediction is trustworthy for the patient that I'm interested in applying it to? And consistency in a very specific sense. Is it consistent with the body of literature that exists about medicine? So consistency again, does a model yield predictions that are in agreement with well-validated domain knowledge? So medical literature has evolved over 250 years. It's about when the first medical school was around 255 years ago. And over that time, there are some clinical phenomena that have been well validated. We have an innate immune response. We have T cells. We have B cells. We know a lot about the heart that has been well validated over centuries. And so consistency with these well-validated concepts increases a chance that the model will be generalizable to unseen patients, because the model is presented to the clinician as being validated on some well-chosen data set. And it may be even several different data sets, but is it going to really be useful in perpetuity? If it really is consistent with the corpus of medical knowledge that's existed for a couple of centuries, I have a bit more faith that it's going to be useful across many different patients over long time periods. And trust, understanding failure modes. So as we've always said, prior work uses statistical measures of performance. They correspond to averages over patients with a range of different characteristics. And you can't really tell whether from these averages, whether they're actually trustworthy for any particular patient. It's very hard to do that. So trust is about when is a model prediction likely to be misleading. I just want to check with Mark. Am I out of time, or do I have a little bit more?
We are out of time for the first part, but perhaps we can talk about the additional content with our guests that are joining us. Does that sound good? That
sounds great. I do. Yes, that sounds great. I just wanted to, at some point, I will just go over the people in my group who have helped to develop a lot of these concepts.
Sure. Thank you. Go ahead and close out by make a closing statement, and we'll bring on our guests.
So the last part was just a specific example, I think, that illustrated some of this. And my conclusions, the take-home message I think that I would like to get across from this is statistical measures of performance are insufficient by themselves to ensure that a machine learning model will be embraced. And I think that's true in the clinical domain as well as other domains. And to be successful in the sense that it will be adopted and used, it must leverage domain-specific concepts to convince the intended audience that the method will actually be be fruitful. And just the members of the group who I work closely with and who do all of the work and help with these ideas. Thank you.
Thank you, Professor. Yes, we certainly appreciate how, you know, these topics are really a team effort. It takes a lot of not just one bright mind, but many bright minds to make progress on these intractable challenges in AI and in healthcare. So thank you to you and everyone in your group who contributed to the work you shared today.
Great, thank you.
I'm delighted to welcome two business experts to join us for this discussion. So Ron Lancaster directs corporate research at Boston Scientific, which is one of the world's leading medical devices companies and medical devices and diagnostics companies, and is also a member of the MIT-IBM Lab, who we very much enjoy working with because they are so relentlessly focused on improving health outcomes, like patient outcomes, that they are one of the best companies I've seen in terms of actually executing, making progress on these innovation opportunities. So they're really fun to work with. Jianying is my colleague from IBM Research. Jianying is an IBM Fellow, which is the highest technical distinction you can receive at our company, and she is the global science leader for AI for healthcare at IBM Research, which means that she not only works with our lab and the healthcare and life science related work that is coming out of MIT-IBM, but she's connecting dots all over the company, within IBM Research, within Watson Health and our business units, and with companies that we work with like Boston Scientific. So thank you both for joining us. And I understand you heard Collin's talk, so maybe I'll let each of you just comment on it to kick us off. Ron, would you like to go first?
Yeah, sure. Dr. Stultz, that was way over my head, but I got the gist of the message, and you know, I sort of see us looking being in the valley and looking at the top of the mountain, and you know, clinically relevant, accepted diagnostic guidance, you know, seems to me to be sort of at the top. And what we're trying to do within Boston Scientific is start a little lower in terms of guiding intraoperative decision making, combining imaging with pre-op imaging and other factors that are going on real time, and just helping build confidence that what a physician is seeing and what they think they're seeing, the models is bolstering the confidence. And so there's real value in that, especially when you're looking at difficult images. You know, everyone looks at the ultrasound of a baby and they say, oh, you know, but in my head, it's always, is that a boy or a girl? I mean, I can't even tell, right? So, you know, those images come in all forms, and they're very difficult to interpret until you get to your experience level where you just are comfortable and see it and know it. So there's a lot of opportunity, I think, to really build, you know, surgical confidence, procedural confidence along the way. Every time we've looked at EMS and you know, EMR data and say, how do we help guide a diagnosis? It just feels like it's way up there, and that's the problems you're challenging, you know, us with as a community. And so I totally agree with you that it's that's a big hill to climb, and we'll get there. But you know, our company is really trying to just take some steps to help our physicians do a little better job along the way. So, Jenny, sorry, I know we don't have much time, so.
No, we're okay. We can go a few minutes over, actually. You know, this is the last session of the day, and we have some debrief time at the end, so we're okay on time. You know, that gap in explainability that you mentioned, Professor, is really profound. You know, I think there's some frustration you see in the scientific community, the computer science community specifically, sometimes with when people talk about neural networks as black boxes. It's like, no, they're not. Like there's a lot more than we understand about them today than we did 5 years ago. And there's this tool and that tool, but it's like Heisenberg speaking to the literary scholar, right? There's a translation gap, and there's a very real component of effectiveness that has to kind of honor the end user, understand who is the human being who is going to be using this stuff. And I know, Jianying, that's been a big focus in IBM research and IBM more broadly. What lessons, hard lessons and new opportunities have you learned during your tenure working in this space?
Yeah, first of all, I just want to thank you, Collin, for a fantastic presentation. It's a pleasure to listen to you as always. I want to comment, sort of follow up a little bit on this notion of uncertainty and measuring uncertainty in the model as part of that trustworthiness, right, assessment. As Collin, you pointed out, when we started out, everyone was just focusing on measuring accuracy, all forms of accuracy, right? And then we started to realize that's not enough. You need to understand the uncertainty of the model before you can assess how much you can use it. It turns out that uncertainty actually is hard to measure. Everyone knows, machine learning machine learning models very often require a lot of data and a lot of compute power to train. But measuring uncertainty in the traditional way, which involves a lot of cross-validation experiments, requires even more typically. And so one of the areas that our joint team at MIT-IBM AI Lab have been looking into is what are the some alternative ways of measuring uncertainty that would require less computation, less data, and making it more practical. And so this is one of the areas that we have been doing work on, and there's a upcoming paper in Europe on this topic. But Collin, what you touched on at the end takes this one step further even, right? So, okay, these uncertainty models developed at the population level, yes, they are useful for us to design population level, policies and programs, but still they're not sufficient for point of care decision support for the individual, right? So for the individual, I think what you're getting at is you really need to understand for this specific instance, how much confidence I have in that model, right? So, and so that's really, taking this, that work really feels that the work that you described is filling that really important gap. And I'm wondering, Collin, what's your view in terms of what are some, you showed the MI claims checklist that was recently published. And again, that's describing more the model at the population level. How do you trust the model at the population level? Now, if you were to think about, similar things, but for models that can be used at point of care for individuals, in your mind, besides this, the uncertainty at the individual level, what are some of the other important things to check before you can determine, whether that model can be used?
Right, and I want to say this also touches on some of the things that Ron mentioned as well. So just to tie these comments together. So intraoperatively, or let's say with any procedure or any sort of intervention, it's useful to know not only what you should do, but what would happen if I did this and it was the wrong thing to do, right? So I think that the discourse has to be a bit more complicated. When clinicians, when we think about making decisions, we think about what's the probability that this will do something good for the patient, and what's the probability that something good to the patient will happen if I did nothing. Right? It's always weighing options and via probabilities and making an informed decision that way. A clinician, I think also for lots of patients, there is some art involved that comes from knowing the patient, speaking to him or her, speaking to the family. Well, if I do this, there's maybe 5% of stroke, but I know that this person does not want to have a stroke, right? He watched his mother die from a stroke, right? And so, and allowing the clinician to be able to factor in those quantitative aspects with those other sort of is really important. So I think that in making tools that one would like to enter the clinical workflow, these things have to be considered. And in terms of this, so there's the, and now getting back to Dr. Hughes, fellow Hughes comment, we have, making a statement at an individual, for individual patient, is this good for that patient and for a population? There are intermediate stages there. So for example, there are subpopulations one can define where performance is poor, right? And so what subpopulation does a given patient belong to? That's sort of one intermediate way of sort of estimating the uncertainty as you get. And I think there are more complicated ways that one can use. We have done some work looking at estimating individual treatment effect with confidence intervals, and that involves some generative modeling where you can actually generate patients that fit certain criteria. So I think there are ways that one can span the spectrum. Yeah. But I think the overarching point is, as has already been mentioned, is that just the simple metric, this is where things fail horribly in terms of providing a set of inputs, and that requires talking to the clinicians. What do you consider when you are making a decision with the patient?
Yep.
Even in the OR, what sorts of things are dispositive in your view? And then the clinician articulates it, and that has to be part of the human-computer interaction.
Mm-hmm. It speaks to the fact that, whether it's in healthcare or in lending or in any aspect that really influences our life, nobody wants to be treated as a statistic. They want to be treated as a person, and they want to be seen in their unique circumstance and cared for in their unique circumstance. And that's what doctors want to be able to provide their patients and need to be able to provide to their patients. And it's interesting how, these topics and themes of quantifying uncertainty, individual treatment versus group treatment, subgroup outcomes versus, larger group outcomes, and how we define those and how we reason about those. We're seeing these key themes traverse across these stages, and the explainability component of building trust has to go hand in hand with that. So yes, we understand failure modes, and we can reason about and calibrate our risk based on risk tolerance. But we have to walk with people along that journey and not ignore the things that are important to them. Ron, to close us out with this discussion, as a company that is who's in the business of saving lives, who's in the business of improving health outcomes, I'm wondering if you could speak to this theme, and how you project your own company's path forward in terms of AI we can trust. Where are we on that journey, and where do we need to get to?
Yeah, it's a great question, and my crystal ball is pretty foggy, but I will say that where I'm seeing confidence and change is in image recognition, so you can take that to your radiology and in diagnostics in that regard, but also in pathology, right? So you start to build models that screen out the obvious, and the pathologist starts to build confidence that the model is not taking away something that they should have caught. And then you start translating that to technology that's going to start giving us, real-time visual, molecular level interpretation, so that the physician real-time is going to have the ability to diagnose through the models exactly what they're seeing, right? Now, most cases you want to talk to the patient before you go into a treatment if you see cancer, that sort of thing, right? But in between there, I do see us transmitting data real time to the pathologist and getting that legal confirmation that what you're seeing is what you think you're seeing, good or bad, right? And but down the road, it's not, so I see a full, and not that far out, I see a change in pathology as an example where, pathologists are going to start becoming much more machine learning people and guiding, you know, the models and the development and the accuracy and the, you know, so, you know, that I see that as a direct application that's coming. When we look,
so we have a merging of disciplines and, you know, more people who can speak both languages.
Yes, exactly. And you know, when we look at our operations line and we replace human inspections, which, you know, we're trying to minimize our labor costs, right? And we're asking our models to say, okay, be 100% confident, but we only expect you to hit an 80% mark, right? So now our labor went to 20% on those inspections, but we know everything the model told us that went through as a quality product, right? So we can afford to back up step by step where we expect the models to eventually equal the capability of the process to deliver a good part, right, each time. So taking that sort of same concept, build confidence in the interoperative procedure and guiding, and probably more at the learning stage, and the people like at ERCP procedure where you've got a really difficult cannulation to make within a very tight space. And there's a lot of damage done if you don't get it right, right? So, you know, I think to me it's kind of the same. We're just applying these technologies to different levels, and then, you know, in our facilities we can readily see it, but it's kind of the same thing when we translate it to, you know, looking at this anatomical structure and presuming what's on the other side and taking some images that help, okay, it should be at 11 o'clock, it should be, right? And let them make the decisions along the way, but guide them. So that's,
and I remember when we visited some facilities as guests of Boston Scientific, you know, standing over the shoulder with clinicians looking at angiograms, and it's difficult for us to figure out what's going on. It is not a trivial task, and it's going to take a lot of work to get there, you know, especially as we think about just ways of doing things, ways people were trained, you know, when they came up through in medicine, and being reconciled with the technologies that are available to us today, and that has to be a tight feedback loop to develop new tools and techniques.
And I'll add, Mark, that you picked the perfect example where it's difficult to get your ground truth figured out, right? Because if you get certain images, particularly in a 2D stage, you know, you put that in front of 5 physicians, you might get 5 different directions drawn on the piece of paper, right? Because it isn't what they see and do. They see, and they microsecond decision making, they change along the way, but they don't. That doesn't get interpreted when we're trying to get our ground truth, and what they're seeing isn't reflective of the real world situation. So it's really hard, you know. And those angiograms, I'm just I'm with you, Dr. Stultz, all yours. You know, thank goodness.
But outcomes though are much more objective, right? And you know, I think that's.
You don't have variability like what time of day did the clinician look at this at? Are they tired? Have they had 2 cups of coffee or no cups of coffee yet?
Our human inspection data, you know, around the world, we know that Mondays are different than Wednesdays and Fridays, right? That's we know that post holidays are right. So humans
are Friday at 5 p.m. is different than Monday at 8 a.m. Right.
Yep. So I try to get my surgeries at 7 in the morning.
Yeah, so when we talk about social determinants of health, it's not just patients, it applies to the physicians too. There are social and behavioral aspects of it.
Yeah, and navigating that complexity is why we all have to be in communication with each other across industries, you know, where medical doctors have to be in communication with medical device companies and in communication with research scientists and businesses. You know, we bring different perspectives so that together we can unpack that complexity and navigate, you know, toward a better future in healthcare and indeed in every industry. Well, Ron, it really is a pleasure getting to work with you and your colleagues at Boston Scientific. I'm inspired by the work that you guys do and the approach that you take, and we're looking forward to the upcoming year and couple of years of collaboration. Dr. Stultz, it's a real honor to be able to fund your research through the lab and to have our scientists connecting with you and your students. We're very, Jianying and I and our colleagues at IBM Research are extremely grateful to get to work with you.
Well, it's been a great experience for me personally, as well as for the students I'm honored to work with. So thank you, guys.
Thank you. So to close us out, we're going to transition and welcome back our directors, Aude Oliva and David Cox, to just have a debrief on today's session and a look ahead to next week's session on AI we can scale. So David and Aude, thanks for joining us.
Thank you, Mark.
Great, thanks, Mark.
So Jim, yep, there we go. And so yeah, we've had a number of talks today. Weng on certifying robustness, Misha Yurochkin on algorithmic fairness, Armando Solar-Lezama on safe reinforcement learning, and Collin Stultz on clinical risk models. What stood out to you guys? What was the highlight for you from those talks, or certain threads that you saw between the talks?
Well, certainly for me, I feel the urgency to really look carefully when any system starts being developed in a lab or is deployed at scale, systems that we can trust, that are accountable, that are robust, that are safe, that are transparent, that care for people and care for what they are doing. I see like two urgent issues that as a community, both in academia and industry, we really need to look at, is define the principle to integrate the decision about ethics and risk into the AI system, and train people. We have this opportunity to train bilingual software engineer in academia that will be computing and social responsibility, computing and medical impact, computing and autonomous system. And those, we are going to send them to industry. They are going to go and find a job and really help the society at large to really be careful with the deployment scale, which basically tell us that there's a lot of job coming up. Those are needed.
Indeed, and as you said, it's like depth in a certain discipline is important, but we need to be able to walk in both worlds and talk to each other and not develop things in silos. And that was one of my takeaways too, especially from Collin's talk. To understand that, listen, we can develop all these methods and all these algorithms, but if we can't talk to one another in the real world settings, if we don't have traversing of discipline and traversing of shared terms and understanding, then the algorithms we develop won't be well informed. They won't work well for the way that they need to work. And two, they will never really be implemented because there's just too much of a gap. There's too much of a communication and understanding and requirements gap. And so I think that the topic of trust, it's interesting. In like personal relationships, we know that the topic of trust is a large part is communication, right? It's communication and what you do consistently over time. That's how we build trust with each other. And the same things goes with the way that we interact with this technology. Mm-hmm. David, what stood out for you from the day today?
Yeah, one thing I think you can draw a line.
Well, we seem to be
through all of the talks, which I think is interesting. When we talk about trust in AI, there's a question: who is trusting, and that really has to do with the user. And I think implicit in all this is this talking about technology, but we're talking about how the human interacts with that technology. And it's really fascinating. I think healthcare is a great, because that's a case where, you know, the stakes are obviously very high because human health is at stake. But you know, many of the things that Collin talked about in terms of how do you interact with an end user transcend any one particular application area. So I think we're having some internet issues.
We are, but we're getting the gist of what you're saying, and I think it's an important point. Yeah. So you know what David was saying is, you know, oh, there you go, David. Do we have you back?
Yeah, I think so. Always wait. The internet always waits to screw up right when I'm talking.
Yeah, it's okay. But, we got the gist. I think, you know, we got the gist of it. But feel free to continue.
Yeah, no, I just think that idea that when we build AI systems, it's very easy because we're focused on the technology to ignore the human element of it. And I think what's important when we think about what's next in AI and we think about how we actually get the benefits of AI, it's really important that we always include that human in the equation, and really target to who needs to trust this. Why do they need to trust this? How do they be part of the discipline of validating those systems, understanding them? And I think that needs to be a guiding star for the research we do. And certainly that is a guiding star for us at the MIT-IBM Lab, both on the MIT side and the IBM side, really asking how do we augment humans, how do we integrate with them, and really consider them as part of the equation. I think that we keep our eyes on that as a research community, I think we can do some pretty amazing things.
I agree, and that's a great place to wrap up the day. AI we can trust. You know, in conclusion, you know, part of it is quantitative and quantifying uncertainty, quantifying predictions and robustness. Part of it is deciding when to use AI and when not to use AI. A big part of it is explainability and communication. But ultimately, all of these things have to be grounded in a person-centric approach that listens and regards the needs of the human beings who are using and interacting and relying on these systems to achieve a certain outcome. And I think that's what the theme of AI we can trust really drives that. Next week, we'll be talking about AI we can scale. So this is understanding that, hey, you know, there are opportunities to do powerful things, and settings where the trust is manageable, where risk is manageable. But the sheer computing infrastructure and architecture and cost involved in modern neural architectures is quite extraordinary. And it's also very difficult to train systems that are robust. There's a cost component to trust. And in developing robust models. So next week in AI we can scale, we're going to hear some great talks from our research scientists from MIT and IBM Research who are leading the way on that important topic for actually executing AI in a real world setting. So please join us 9 a.m. Eastern to 12 p.m. Eastern next Thursday on the same channels. We'll be broadcasting on YouTube and other live streams, and you can sign up for Eventbrite. And we encourage you, if you tuned in today and you liked the content, please share it, and we'll invite more people back next week. Thank you very much.
Thank you.
Thanks, everyone.